Bonjour, bonjour, bonjour à tous. Welcome, everybody. I think we can start now, if you agree. Let me start by saying that. Oops, no, it was nice. Okay. We are of course very happy to have you around today. We realize that coming to this event today was not necessarily an easy decision to make for you to make. And we want to thank you very much on behalf of the organizing committee. Thank you very much again. So as you know, this virus is still quite active in France, and we have to ask you to keep the mask on while in the room. There is also some hydroalcoholic gel available here and there, so please use it without limitation. Don't drink it. We are about half capacity here in this place. So please make yourself at ease, occupy all the space. Also, we will have a half an hour break in about 2 hours, during which we will ventilate the place as much as we can. So hope things will be okay. So we've set up things so that those who could not come with us today will be allowed to, will be possible for them to follow the talks online. Unfortunately for the presentation also, a few of the speakers could not come in person today, but of course we have them give their talk remotely. This is true for our Japanese friends, Hitoshi Murayama and Takaaki Kajita. They could not come to Paris and they will give their presentation in a few minutes. And it's also true for Roger Blandford, who actually was in France a few days ago, had to come back to the US, but could not come back here. So he will also give his presentation in Zoom. All right, so all the other speakers are here, so that's very nice. Thank you. All right, before we start with the talks, let me say a few words about today's event. So, as you know, 50 years ago, the French government created IN2P3 as a National Institute for Nuclear Physics, Nuclear and Particle Physics. And of course it did so in order to develop the French activities in those fields. The ambition was that by federating university labs and CNRS labs, France would be able to contribute more on the international stage in particular, since, as you all know, I mean, our science is very international, it has to be. It often requires very large, equipment, investments, and of course, we also benefit a lot from altogether, international partners working on these large projects. So we think in France, of course, we think that the last 5 decades have shown that the relevance of this vision, with IN2P3 being, part of major discoveries that have happened in the last 50 years. Now, to mark this anniversary, our labs in France have organized local events, local celebration events, very nice. Some of you maybe have participated, but we also wanted to have today a special one, a special event, where we would invite our partners, international colleagues, to join us and celebrate around a few talks. And of course, we also wanted to celebrate around a few glasses of whatever it is. But this, however, turned a bit complicated because of the virus. I'm sorry about that. We just received instruction today, this morning at 10, that we have to cancel all festive moments, events. So I'm very sorry, we will not be able to share a few drinks and food. This is really a pity. However, we managed to maintain the walk through the exhibition part and the visit of the Grande Galerie. And you will haven't be able to walk out with a bit of food and maybe drinks. I don't know exactly yet if that's happening. Okay, so 50 years is quite a long time. And of course, a lot of progress has been made in our field of research, which actually has involved into including particle astrophysics and cosmology, so we'll hear about that as well today. We didn't want, however, really to embark into a review of all the important achievements and results that have happened in those years, but rather to reflect on them. So the idea was to reflect on what has been achieved, of course, but also look a bit forward in the future. So for that, we've asked a few colleagues, well-known experts in their field, to share with us today their view, their personal view on their field of research, to tell us what they think we know, to tell us also they think we do not know, but also, of course, maybe even more importantly, to share with us their best guess about what comes next, the unknown, the unexpected. So without waiting anymore, well, before I say that, I have another small instruction to give you here. For those who do not want to be filmed or now being photographed, please, you can sit at the back of the place, of the amphitheater here, so that you don't get filmed. And if you really don't want to be photographed either, just tell the photographer who is here taking photographs that you don't want to be, and we'll take care of that. Okay, so without waiting more, let's start with Professor Hitoshi Murayama, who will tell us about the physics and mathematics of the universe. So Hitoshi, can you hear me?
Yes, I can hear you.
Ah, very good.
Let me try to share.
Thank you very much.
Try to share the screen. Okay.
Good.
Oops.
Yes.
No, this is not what I wanted to do. This one. Does it look okay?
Okay. So please go on.
Yeah. Okay, so let me get started. So bonjour, madame et monsieur. I'm Hitoshi Murayama from UC Berkeley and Calgary ITMU. And I was slow in deciding on the title. So this is the title I was given by the organizers. It's such a nice title, so I decided to stick to it. And first of all, the congratulations to this community for having this 50th anniversary of IN2P3. And as Reynald already said, the 50 years is a long time. 50 years ago, we didn't believe in quarks. We didn't have an anisotropy in CMB. We haven't even heard of inflation. And since then, of course, a lot of progress have happened, and partly thanks to the scientists at IN2P3, all the way going from Gargamel to Atlas and CMS, Eros, Planck, Supernova Legacy Survey, now DESI. So I really congratulate you all, and also congratulations to all of us around the world for this festive occasion. And I really missed being in Paris. I really wanted to come here, but I had a prior commitments that prevented me from traveling. But now that I heard that there wouldn't be any drinks anyway, I feel less bad stuff. Anyway, so within these 50 years, we established 2 standard models, which is a tremendous achievement. So on the particle physics side, we had this framework called a standard model that started around 50 years ago. And now we filled in this last missing piece of the Higgs boson. And on the cosmology side, we have now this bizarre particle content as indicated by the Planck data, which established so-called lambda CDM paradigm with a power or density fluctuation, which presumably come from the inflation. So this is something we should really pat ourselves on the back. This is a huge accomplishment for a human being. And I really like this logo of IN2P3, that's this lettres infinies, was stretching all the way from infinitely small to infinitely large, I believe. And this is actually a wonderful logo to indicate the establishment of these 2 standard models. So having established both of them, I feel it's really time to go beyond them. And to go beyond them, my personal feeling is that 2 of the latest discoveries we have made, namely Higgs boson and gravitational wave, will become very important new tools for the discoveries. The reason we believe that we can go beyond the standard paradigm is at least we know there are 5 things we are still yet to understand. The dark matter is not baryons, made of something totally different. Mass of the neutrino, Professor Kajita will be talking about this in my next talk, and that's also a physics beyond the standard model. Dark energy that's stretching the universe in accelerated fashion. We don't know what that is. And looking at anisotropy in CMB, then we know that the photons coming from one end of the universe and the other end of the universe seem to be correlated, even they should not have talked to each other. That seems to violate causality. And now we attribute this idea to inflation. Now that every part of the universe were together at the very beginning, they were all correlated back then, but they got separated by this incredible expansion. That's why they are still correlated, even though they are apparently in a causal distances. And if you attribute this idea to inflation, then it's a big reset button to the universe. So now we know the baryon asymmetry of the universe cannot be the initial condition. We have to have a mechanism to create this baryon asymmetry after the inflation. In most of these cases, we don't really know their energy scales, but nonetheless, we can think about where they might be coming from. And today, I'd like to focus on this last bit of the baryon asymmetry to get started, but I end up touching on many of the other aspects as well. So the idea of the baryon asymmetry is that when the inflation turns its energy density into radiation, then equal amount of matter and antimatter is created because the energy turns into the same amount of matter and antimatter as we know from the laboratory experiments. But if it stayed that way, eventually matter and antimatter would meet and they would all disappear and the universe would be empty. So there's nobody in the hall today to celebrate this occasion anymore. So something must have happened, namely that there must have been some process that turned, let's say, 1 out of a billion antimatter and turn that into matter instead. Then there's a tiny imbalance between matter and antimatter so that when the matter and antimatter eventually met and annihilated, pretty much all of them did disappear except for this tiny imbalance, and that's us. And that's why we exist today. So what could have been this process that reshuffled the amount of antimatter and matter is the real question that saved us from the complete annihilation. So there was indeed a superhero who saved us from this complete annihilation. And we as a community have been talking about mostly 2 directions who this Superman could have been. And one of them has to do with the electroweak scale physics. And another one has to do with the neutrinos. So let me get started with the first idea that something must have happened near the electroweak energy scale. So looking at this pie chart again, we always talk about the puzzles, what dark matter may be, what dark energy may be. But as I said already, we actually don't know why baryons exist. So we actually don't know anything about any of these 3 elements in this pie chart, which is kind of amazing. And we also are puzzled, for example, in the case of baryon and matter, both of them behave as matter, so their ratio remains constant. But why is this numbers so close to each other within a factor of 5 or so, if they come from totally different origins? So perhaps the baryons and dark matter have the same common origin, and that is the idea called asymmetric dark matter. So maybe the dark matter and the ordinary baryons come from the same origin. So what that means is that in addition to the standard model, we contemplate another sector, which is often called the dark sector, which has its own particles and its own interactions. And we are looking for how these sectors would talk to each other. And one of them is called the neutrino portal, namely the sterile neutrino can talk to leptons in the standard model, and also lepton-like particles in the dark sector. There may be a kinetic mixing between our photon and dark photon. And our Higgs and dark Higgs may also mix with each other. So that's the way we can get some information about what may be going on in this dark sector. So it's one very simple idea how everything might have happened along this line of thinking. So we have the standard model of SU2 cross U1 at the electroweak scale and SU3 at the QCD scale. Just imagine something very similar in the dark sector, and let's say just one generation of dark sector for simplicity. And also imagine that electroweak scale in the dark sector is a little higher than ours. And this electroweak sector has a first order phase transition, maybe with the 2 Higgs doublets and CP violation in it. And when you have this dynamics of the phase transition and you have particles colliding, the expanding bubbles and so on and so forth, it is known that you can generate the equal amount of the baryon and lepton numbers, but in this case, those asymmetries in the dark sector. By using the sterile neutrino portal, you can let these dark leptons decay into the standard model leptons. But within the standard model, the lepton numbers can further be converted to baryon number due to what is called the sphaeroron process of the non-perturbative electroweak phenomena. So we know that exists, and therefore you can generate the baryon number. On the other hand, the baryon number in the dark sector still remains the dark sector, and eventually the baryon number carried by the light up and down quarks in the dark sector will be confined into baryons and pions. And some of these pion states would decay into the standard model particles through this mixing of the dark photon and photon. So what remains the dark sector in the end is the only asymmetric component of dark baryons. So these dark baryons are therefore dark matter. And they come with the same origin, namely they start out with the same asymmetry that would give us this baryon asymmetry we rely on for existence. So they come from the same origin, then no wonder their masses and contribution to the pie chart are similar to each other. So that's the way we might explain this deep puzzle. But once you actually set the model this way, there are so many connections that can happen between the dark sector and us, starting with the Higgs sector, neutrino, and the photon. And when you produce, for example, Higgs boson at the future Higgs factories, they can decay by mixing into the dark Higgs that might go into dark photon, that kinetically mixes back to the standard model, going to highly combinated pi plus pi minus and mu plus mu minus, which is kind of difficult to see at the LHC environment because of so much material in the detector. But once you go to future E plus E minus machines, these become a very clean signature. And you can even think about really complicated decay channel from this dark sector dynamics, which leads to a lot of missing energies together with some visible energies at a very low masses. So this kind of the sector can be probed then from mass-producing Z boson decaying to stereo neutrinos and mass-producing Higgs boson that decay into these exotic modes or invisible Higgs. And many of these modes can be explored some 4 orders of magnitude better than the high luminosity LHC. So that's something we really would like to do in the future. So this is what I meant. The Higgs boson, that's one of our latest discoveries, can become a tool for more discoveries that we can understand physics the baryon standard model, namely the origin of the baryon asymmetry and the dark matter. And not only these high energy experiments are important for this, but also direct detection experiment and beam dump experiments will probe a swath of the parameter space for the dark photon. And when the asymmetry originates in the dark sector and gets transmitted to the standard model, then we predict the mass of the dark matter is something like 1.5 GeV, which is kind of light for direct detection experiment, but thanks to the new development of Migdalow effect, you can actually look for that as well. If the dark matter is dark neutron, that's a little more difficult because it doesn't interact with the dark photon, but still beam dump experiments and LHCb can probe the parameter space for dark photon. If the asymmetry originates on the standard model side instead and get transferred to the dark sector, then direct detection experiments have much better reach into this parameter space, and you can even probe a little bit of the dark neutron because dark neutron can carry electric dipole moment, which is not possible in a standard model, but it may be happening in the dark sector. In addition, there is this new QCD in the dark sector, which you can probe by E plus E minus experiments, where you detect one photon whose energy you can measure, and the other photon then mixes into dark photon and can go into some of these dark resonances of the dark QCD, dark rho, dark phi, dark psi, dark epsilon. And by measuring the energy of the visible photon, you can tell the mass of this invisible sector. And therefore, you can do spectroscopy of this dark QCD, even though you don't see anything in principle. And this is just one example that if I assume the dark sector to have similar resonance spectrum as in the standard model, this kind of monophoton search can lead to these peaks of dark J psi, dark psi 2s, dark phi. So with this kind of spectroscopy, you can even in principle work out what the gauge group of the dark sector may be, how many colors they are, how many flavors they are, what their quark masses are based on this kind of data. So you can really have the opportunity to probe dark sector by combining these many different probes all the way from high energy machine, beam dump to low energy machines like Bell 2 and direct detection experiments. So that's how we hope to learn a lot more about the dark sector. So that's one possibility where the baryon asymmetry originates somewhere around the electroweak scale, and the Higgs physics really plays a prominent role as a tool for the next discoveries. On the other kind of scenario, where the superhero is actually neutrinos, then we have a totally different approach because then we're talking about very, very high energy physics.
The reason why neutrinos are interesting, as I'm sure the next speaker would talk about, Professor Kajita, who discovered the mass of the neutrino, we know the neutrinos are very light, at least 6-7 orders of magnitude lighter than the lightest elementary particle we knew, namely the mass of the electron. So there's definitely something special going on with the neutrinos. And the best idea to explain this is the famous seesaw mechanism. So we try to understand why the neutron mass is finite. Now we know it's non-zero, but why is that so small? And why we thought the neutrinos must be massless before the Kajita's discovery is because experimentally, all the neutrinos we have seen are left-handed. And as long as they are going the speed of light, this is a frame-independent concept, and they are always left-handed. There's no problem with this. But now that we know the neutrinos have mass, they are not going the speed of light. So especially if there are young people in this audience, they may be able to run faster than neutrino and look back at the neutrino. Then in your reference frame, neutrino is moving backwards, but spinning the same way. Therefore, it looks like it's a right-handed neutrino, which none of us have seen before. So that's the puzzle. So as long as the neutrino didn't have a mass, that was not a problem at all because nobody can go faster than neutrinos that are going with the speed of light. But now that it's not, then this becomes a real puzzle. So at least we seem to need to introduce right-handed neutrinos to the theory. So in addition to the left-handed neutrinos that can have the electroweak interactions, we also introduce the right-handed neutrino with the Yukawa couplings between them. But if you do so, this is exactly the same mechanism that, for example, electron will pick up the mass from interacting with the Higgs boson that's stuck in the universe today, and we would think that's way too large. So the seesaw is down this way. But what's special about the neutrinos is that right-handed neutrino doesn't need to get a mass from the Higgs because it's totally neutral under all the standard model interaction. So it can, in principle, have a mass of its own. So it can be much, much bigger than the electroweak scale. So we put in another mass down here in this matrix. That's a big mass over here. That would turn the seesaw the other way. And therefore, the neutrino becomes very light as a result. And that's how we might understand why the neutrinos are so light. And once you subscribe to this idea, then this right-handed object you see when you look back at the neutrino actually turns into an anti-neutrino. So you see a neutrino, you take it over, look back at it, then you see actually an anti-neutrino. So that's the way the matter, neutrino, and antimatter, anti-neutrino, can turn into each other. And that gives us a hope that we might understand how the neutrinos might have reshuffled the amount of matter and antimatter in the early universe. So that is the idea called leptogenesis. The right-handed neutrinos are assumed to be very heavy, but in the early universe, when temperature was very high, they must have been produced copiously. And once they're produced, they must eventually decay. And due to this Yukawa coupling, these right-handed neutrinos would decay into ordinary neutrinos in the Higgs. At this stage, the decay branching fractions would be 50-50, and you have no gain in the difference between matter and antimatter. But once you include this one loop diagram and look at this absorptive part, that would interfere in this decay rate when you add them together and take absolute squared. And that would give you what is called the direct CP violation, so that the branching fraction of the right-handed neutrino into ordinary matter and antimatter can be slightly different from each other. So once those right-hand neutrinos are produced, all you have to do is wait and let them decay. And once they decay, you end up with a different amount of matter and antimatter so that we can survive the great annihilation. And in fact, this kind of direct CP violation has been now seen with Bohr experiment and also with Bell, again, with a contribution of scientists from IN2P3. So we know such a thing can happen in the real world. And so that's the idea which has become the dominant paradigm in neutron physics today. But in order to see if this is really true, then we need to have a probe to very high energy scale. And this idea is known to be notoriously difficult to test. If you work out quantitatively, what kind of the mass of this right-hand neutrino would make this scenario happen, then it turns out to be somewhere between 10 to the 10th GeV and 10 to the 15 GeV, indeed the very, very high energy scale. So that becomes almost impossible to reach experimentally. On the other hand, this horizontal axis roughly corresponds to the observable mass scale of the neutrinos. And what Kajita observed in the next talk, it corresponds to something like 0.05 electron volt. So the range we're talking about is really similar to the observed energy scale of the mass of the neutrinos. So that's a non-trivial success that gives us some hope that maybe this is indeed the right way to think about the origin of the baryonic asymmetry and therefore origin of our Egon existence. But how do we test it? And of course, the best way to test it is to go about and build a collider that will reach a 10 to the 14th GeV. And by extrapolating the current technology, the size of the collider would be about this big. That not only requires a very close international collaboration, but presumably also interplanetary collaboration. That is a long way off, I'm afraid. And that will be ultimate future circular collider. So unfortunately, I don't think I'm going to see this within my lifetime. So it is notoriously difficult to test indeed. And that's where I would propose that what we can do is what I call archaeology. In archaeology, you don't redo the history. But what you do is by digging up enough artifacts and fossils, you can come up with many different kinds of circumstantial evidences. And if those artifacts would line up to tell you the consistent story, you start to believe in that. So what are the circumstantial evidences behind the seesaw mechanism in leptogenesis? One of them requires very delicate nuclear physics experiment of the neutronless double beta decay. Another one, to see the evidence that CP is violated in the neutrino sector, we look for CP violation in neutrino oscillation. And also that now that we know the lepton flavors would also mix, we would love to see lepton flavor violation among the charged leptons. So these are possible circumstantial evidences. But in the spirit of archaeology, it's all the way the better if we have the more circumstantial evidences. So how do you come up with them? And I don't need to tell this audience that the neutronless double beta decay is an active effort in the French community looking for the transition of the beta decay, turning a neutron into proton by emitting an antineutrino. But if this antineutrino actually can be absorbed by neutron, then you can actually have another turn of this neutron into electron without emitting a neutrino in the final state, hence neutrino-less double beta decay. We know the lifetime of this kind of process is very long, like 10 to 24 years and beyond. So that requires a lot of patience, but that's what people are doing. And we now actually zooming into this parameter space from above using double beta decay, and also from cosmology, starting with the CMB and future galaxy surveys like PFS and DESI. So that's how we are narrowing in the parameter space. I understand that IN2P3 scientists are involved both in hyperchemiocandide, looking for CP violation in the neutrino beam from J-Park, and this is the potential signature of CP violation. And also in Dune in the United States, that would also give us potential signature of CP violation. Then we know we have the circumstantial evidence of the CP violation in the lepton sector, as well as lepton number violation from neutronless double beta decay. But we would like to see more circumstantial evidence. My recent proposal is the following. Even though right-hand neutrino is so heavy, from 10 to 10 to 10 to 15 GeV scale, still it's not quite as heavy as the Planck scale of 10 to the 19 GeV. In addition, because we believe in inflation, this mass scale has to be below the inflation scale. So in some sense, this right-hand neutrino scale has to be suppressed compared to the ultimate scale of physics, like Planck scale and inflation energy scale. So then it is actually quite natural to think that the mass of the right-hand neutrino is induced by a similar Higgs mechanism like in the standard model. For example, if you gauge B minus L symmetry, the right-hand mass neutrino is actually forbidden by the gauge symmetry. But once the gauge symmetry is broken, then the Yukawa coupling would induce the mass of the right-hand neutrino. Then this scale is naturally much smaller than Planck scale and inflation scale. which then means that there have been some new phase transition below the inflation scale. And that phase transition might give rise to the gravitational waves. Indeed, if you think about many different theories based on grand unified models, where you have some grand unified gauge group up here, which keeps breaking down to the standard model, you can think of all kinds of different symmetry breaking patterns. But in all of them, there would be a phase transition that would generate the mass of the neutrinos. And many of these phase transitions are associated with the topological defects like cosmic strings. And when cosmic strings are produced, then they are produced in this kind of a complicated network of the magnetic fluxes, just like in type 2 superconductors. So they are literally flux tubes of the magnetic field of, let's say, your Beeman cell gauge field. And these flux tubes are long and complicated. But because the energy of the tube is proportional to its length, this complicated network tries to simplify itself to minimize its length. But as the universe expands, new strings come into the horizon from the outside, so they're complicated again. So universe has to keep simplifying itself this way. And that's why this leads to sort of self-similar behavior. You have sort of a scale invariant situation. Any snapshot of the universe seems to show sort of similar structure of the cosmic string network. And that's the reason why cosmic string network is believed to give rise to scale invariant spectrum of gravitational wave. And that's a big boon, because when the cosmic strings are born, that corresponds to a very early universe, that will correspond to a very high frequency of gravitational wave, which we don't have technology for. But because of the scale invariant nature, you expect many decades of the frequencies of the gravitational wave, giving to a similar signature. And this range of the masses I talked about, from 10 to the 10 to 10 to 15 GeV, gives you the gravitational wave signal, which is at least reachable in some of the future missions, including BBO and DISIGO in the future, starting with LIGO, Virgo, Kagra, and Cosmic Explorer and Einstein Telescope, and so on. So in principle, we can see this gravitational wave as yet another circumstantial evidence of the seesaw mechanism in leptogenesis. In some cases, this phase transition may come together with the inflation as well. So there's a very nice model by Wilfried Buchmüller, Valerie Domke, and Kai Schmidt that combines supersymmetry and inflation into a single model. Inflation ends by breaking this U1B- symmetry, thereby generating the mass of the right-handed neutrino, which leads to leptogenesis in a seesaw mechanism. And this phase transition does produce cosmic strings, which is the tube of the magnetic field. But in this case, the scale of the symmetry breaking is so high at the inflation scale, it looks like the gravitational wave may be already excluded by the pulsar timing array. But if this theory is part of the grand unified theory, as you know, the grand unified theories actually predict magnetic monopoles, and this magnetic flux tube can be cut by creating a virtual pairs of magnetic monopoles into pieces, and then that would actually let each of the segment to shrink and disappear. So it turns out that there is a cutoff in the frequency spectrum of the cosmic strings. So before hitting this limit from pulsar timing array, the cosmic strings can disappear if the scale is right. And if the scale is even better, then you might actually get the slight hint for the gravitational wave currently suggested by pulsar timing array. And not only that the strings can be cut by magnetic monopoles, and monopoles can then eat the strings. Strings can connect monopoles and devour them. And you can also have different scenarios where you have domain walls, which can fill strings and devour strings, or strings can punch holes in walls and eat them up. In these cases, you generate a different kind of the gravitational wave spectrum, which clearly can be distinguished from the standard spin-string spectrum, or even in the case of magnetic monopoles. So this way, gravitational wave not only gives us signature of these phase transitions, but in principle, we may be able to prove the grand unified theory with the circumstantial evidences. And now that we are talking about one kind of topological defect eating another kind of topological defect, I recently put out a paper with the title Gravitational Wave Gastronomy. And that's really the common interest for people in France and Japan, really appreciating this gourmet gastronomy with a very fine presentation of this excellent food. So that's a common subject for all of us, and so that we can now probe, in addition to baryon asymmetry, to the neutrino mass, dark matter, and inflation, using these new tools we have now with the Higgs and gravitational wave. Namely, if you want to look at what was going on at the very beginning of the universe, CMB photons can go this far, looking at this last rescattering surface. But gravitational wave can punch through all this dense plasma and can go all the way from very early moments of the universe to us today. So that's why we can learn a lot from gravitational wave. And also in terms of Higgs, we had this mantra in high energy physics to keep going to high and high energy physics, like using LHC leading the way. But now that we have discovered the Higgs, while we are not seeing any new physics at the LHC yet, the one thing we should get started with is really to understand the nature of the Higgs. And using the EFT approach, that may allow us to punch through this cloud to peek at what's going on at high energies. But as I argued today, there's another axis of the coupling constant this way. So instead of going to high energies, we can probe physics, which is more weakly coupled to us. So there may be something very interesting going on down here. And that's the idea I mentioned today of the dark sector and baryogenesis happening here. And many different low energy tools like Babar and Bell, beam dump experiment, astrophysics and cosmology will play the role. But once we have the Higgs factory, that would allow us to probe this sector in this way as well. And eventually, of course, we hope that we literally go through this cloud by going to high energy machines in the future. So the next 50 years, we have many things to look forward to. So I'm very excited about this. So I have already decided that I'm going to live for at least 200 years to watch all this development. So I'm an optimist, as you can see. Thank you for your attention.
Thank you very much, Hitoshi, for this very inspiring talk.
Thank you, Reynald.
We have maybe comments or questions here. Time for a couple of them, if anybody wants to dare. I don't see any hands raising here.
Oh,
again?
That's too bad.
So, any comment, any question? No? All right? No. Okay, so, well, again, thank you very much, Hitoshi. So, okay, so we move now to the second talk. So as we've heard from Hitoshi, neutrinos are getting very central in the future of physics, so we think they are. There have been a lot of change in neutrino physics in the last 15 years. They have masses, they oscillate, everything is happening with neutrino nowadays. So we'll hear more about that from Professor Kajita, who will join us. Are you with us?
Yes, thank you.
Hello, welcome. So please, go on.
Okay, thank you very much. And first of all, congratulations for the 50 years of IN2P3. Okay, let me share my slide. Okay, well, today I'm going to talk about neutrino physics and astrophysics. Well, excuse me. This is the outline. Well, but let me say, if we discuss the neutrino physics in the last 50 years, I'm sure that one of the main topics is neutrino oscillations. Therefore, today, I'll mostly discuss experimental neutrino physics related to neutrino oscillations. And this is the topic I'm going to cover. First is solar neutrinos. The second one, atomic neutrinos and long baseline neutrino oscillation experiments. The third topic is the third oscillation channel. And before finishing, I want to talk about the agenda for the future neutrino measurements. And I'll summarize this talk. By the way, in this talk, I'm going to use this flag to show the IN2P3's contribution to neutrino physics. Okay, the first topic is solar neutrinos. Well, since this is the 50th anniversary of IN2P3, I'd like to remind you the measurement about 50 years ago. About 50 years ago, the pioneering Homestake experiment observed solar neutrinos for the first time. However, there was a mystery. The observed event rate was only about 1/3 of the prediction. So there were a lot of discussions on this mystery, and people called this problem as solar neutrino problem. Then, in the 80s and 90s, several other experiments observed solar neutrinos. One was the Kahn experiment. Another measurements were done by gallium experiments, SAGE and GALEX. And these experiments successfully observed solar neutrinos. But they also observed deficit of the solar neutrino flux. Unfortunately, in the solar neutrino experiments in the 80s and 90s did not give us firm conclusion on what was the cause of the deficit. Then the SNOW experiment came. It is a large heavy water detector. They used 1 kiloton of D2O. And by using D2O, SNOW was able to observe the nu E flux by charge current interactions, namely nu E plus D going to E plus proton, and the total flux by neutral current interactions. Therefore, by comparing these two measurements, SNOW was able to tell us if there are mu plus nu tau flux in the total solar neutrino flux. And if, of course, if there is evidence for nu mu plus nu tau, that is the evidence for solar neutrino oscillations. By the way, in order to observe the neutral current events, they needed to have some tricks, because in the final state, there's no particle that emit Cherenkov photons. Therefore, they had 3 tricks. One is simply to use D2O. Even in this case, neutrons are absorbed by deuteron, and in this case, 6.25 MeV gamma ray is emitted, and therefore they can detect Cherenkov photons emitted by the converted E plus E minus. And in the second phase, they put salt, and then neutrons are absorbed by chlorine-35, and the total energy released by gamma rays is 8.6 MeV, which is substantially higher. Therefore, they get higher efficiency. And finally, in the third phase, they put helium-3 counter, and the efficiency was about 30%. The point was, in this measurement, the neutral current and charge current are measured completely independently. Anyway, SNOW experiment observed charge current and neutral current events, together with the neutrino electron scattering events. And here I show the constraints from snow and super K on the flux of nu E and nu mu plus nu tau. So each measurement have a constraint, and which are shown by colored band. Then you find that these four bands crossed at the point. So these four different measurements intersected at the point, and at this point is clearly indicating non-zero nu mu plus nu tau flux. Therefore, this was the evidence for nu mu plus nu tau flux. And in fact, Snow carried out 3 measurements in the 3 phases of snow, and the data are generally consistent. If they observe the total flux, the flux was just consistent with the standard solar model prediction. But if they observe the nu E flux only, the observation was about 30% of the prediction. So this way, we were convinced that solar neutrinos oscillate. However, of course, there were people who are not 100% convinced. And well, people wanted to have more direct evidence for the neutrino oscillation. And then the data came from Kamland. Kamland is a 1 kiloton liquid scintillator detector, and they observed reactor neutrinos. And Kamland is located here, and there were several nuclear power stations in Japan, and they observed the neutrino flux, and they plotted the survival probability as a function of L over E. Then they found this kind of oscillating behavior. So people were convinced that the solar neutrino problem was really neutrino oscillations. Now, I think the recent highlight is the highlight came from the Borexino experiment. Borexino measured the sub-MeV solar neutrinos. And here, the nu E survival probability is plotted as a function of the neutrino energy. Then the Borexino data really agree with the MSW prediction. So we were again convinced that the measurement of the boron H solar neutrinos, which was about 30% of the prediction, was due to MSW effect. And finally, I just want to mention that Borexino reported the detection of CNO neutrinos as well. And I believe this is really a milestone measurement in the solar neutrino measurement. Okay, now I'd like to move on to the atomic neutrinos and long baseline neutrino oscillation experiments. Well, of course, well, for this audience, I do not need to explain this slide. So I'm going to talk about the atomic neutrinos. Now, in the 80s, there were several proton decay experiments. And these experiments observed many atomic neutrino events. And because atomic neutrinos are the most serious background to the proton decay searches, they had to understand neutrino interactions. And during these studies, a significant deficit of atomic muon neutrino events was observed. Here, I showed the data from Kamiokande and INB experiments. The deficit of muon neutrinos are plotted in this way. Mu over E over delta over mu over E of the data, Monte Carlo. So clearly they observed a significant deficit of mu neutrinos. Unfortunately, Kamiokande and INB experiments were unable to tell us the reason for the deficit. And in fact, we needed a much better, much larger detector, and that was Super Kamiokande. Super Kamiokande is a 50 kiloton water Cherenkov detector, as you know. And now, Super Kamiokande collaboration have about 200 collaborators from 10 countries, including people from IN2P3. And well, Super Kamiokande, from the beginning of the Super Kamiokande experiment, they analyzed atmospheric neutrino events very carefully. And in 2 years after the start of the experiment, they were able to announce the discovery of neutrino oscillations. And here I show the Zinsangu distributions they presented at the neutrino conference in '98. So this is for mu neutrinos, and this is the Zinsangu distribution. One is downgoing, minus one is upward going, and clearly you see the deficit of mu neutrinos, upward going mu neutrinos. So Super Kamiokande concluded that the observed Zinsangu dependent deficit and the other supporting data gave evidence for neutrino oscillations. Now, the Super Kamiokande observation was essentially the deficit of mu neutrinos. And therefore, we have to understand if the deficit is due to nu mu to nu tau or nu mu to nu e. And an important data came from the SHOW experiment. It is a reactor experiment, and this is the sketch of the detector. And they observed the positron spectrum and compared with the expectation. And they didn't observe any evidence for the positron deficit. Therefore, they didn't find any evidence for mu-EVA oscillations. And therefore, they put the constraint on the mixing angle and delta m square. And well, if we take 2.5 times 10 to minus 3, then clearly they constrain the mixing angle substantially. So based on this show result, people generally thought that the atmospheric neutrino oscillation should be nu mu to nu tau. And in fact, there were several experiments that measured atmospheric, nu mu to nu tau oscillations. And there were several atmospheric neutrino oscillation experiments. They are listed here. Also, there were several accelerator-based long baseline experiments. These are listed here. And again, you see IN2P3 is contributing substantially in these experiments, in some of these experiments. And here, I'd like to show the history of the nu mu disappearance measurement in accelerator experiments. The first was the K2K experiment. They observed a deficit of mu neutrinos, and also they observed the distortion of the energy spectrum consistent with oscillations. The second one is the Minos experiment, and they had even clearer evidence for the deficit of mu neutrinos, energy-dependent deficit. And the current generation experiments are T2K and NOVA. And in these experiments, the beam energy is tuned so that neutrinos most efficiently oscillate to other particles. And in fact, the data show a really significant deficit compared with the no oscillation prediction. So clearly, by looking at these data, we see we had really a significant improvement in the understanding of the mu to nu tau oscillations. Well, of course, all these measurements of the disappearance of muon neutrinos, and logically, people thought that the oscillation channel should be mu to nu tau, but of course, we have to confirm. The main player who confirmed the mu to nu tau oscillation was the opera experiment. And here I show one of the candidate tau event. And well, clearly, the opera experiment had evidence for nu tau appearance due to mu to nu tau oscillations. Excuse me. Sorry. In addition, supercameo and ice cube observed the as evidence for nu tau appearance. Okay, now I'd like to move on to the third oscillation channel. Well, since there are 3 neutrino flavors, there should be 3 oscillation channels, and therefore, after the discovery of the solar neutrino oscillations, the main interest of the community was the discovery of the third oscillation channel, and people realized there should be at least 2 ways to observe them. One is the accelerator-based long baseline experiments, other is the reactor-based short baseline experiments. And again, IN2P3 is taking a major role here. And here I'd like to show you the data around 2011 and 2012. In these years, these experiments observed evidence for the non-zero theta 1, 3. So about 10 years ago, we knew that there should be third, we knew that theta 1, 3 is non-zero. Well, of course, the experimental efforts are continuing. And here, I took a analysis result from this reference. And you see delta m square and 3 mixing angles are rather well determined. In addition, we begin to constrain the CP phase delta. Also, the present data prefers the normal mass ordering. Okay, now I'd like to move on to the future neutrino oscillation experiments. Well, future neutrino experiments. Well, okay, here I try to summarize some of the agenda items for the future neutrino experiments. One is the neutrino mass hierarchy, mass ordering determination. Well, the present data slightly favor normal mass ordering, but well, we'd like to be sure about this conclusion. And as I said, the present data suggest non-zero CP violation effect. And as Professor Murayama discussed, the measurement of the CP violation in the neutrino sector should be very important. And this measurement could be related to the baryon asymmetry of the universe. Also, we'd like to understand the absolute neutrino mass. Neutrino oscillation experiments can only tell us the mass difference. Also, we'd like to understand if there are any structure beyond the three-flavor framework. And finally, we'd like to know if neutrinos are really Majorana particles. And today, since the time is limited, I'd like to concentrate on the CP variation measurement in the future neutrino oscillation experiment. And of course, we'd like to observe if oscillation of neutrinos and those of antineutrinos are different. If we observe this effect, it will be, I believe, it will be the first step to understand the origin of the matter in the universe. And there are two big projects going on. One is the Dune experiment located in United States. Another is the hypercamiocande experiment located in Japan. And IN2P3 is involved in both experiments. And Dune and Hyper-K have similar sensitivities, although the experimental details are largely different. And therefore, we'd like to see the consistent results from these two complementary experiments. And in fact, Dune and Hyper-K have quite similar sensitivity in CP vibration measurement. Here, this sensitivity is plotted as a function of CP phase delta. And again, you see both Dune and Hyper-K can have the evidence of, say, around 8 sigma or so, if the CP phase is in the most easy value. And finally, before concluding this talk, I want to mention a new institute, IRANS. IRANS was created on April 1st this year. The funding institutions are CNRS and the University of Tokyo. And the IRANS office is located at the Kashiwa campus of the University of Tokyo. The teams of IN2P3, CNRS, and the University of Tokyo have been actively involved together in research projects in neutrino physics, cosmology, astrophysics, high-energy astrophysics, and particle physics. And in particular, I want to stress that IRANS will be a key laboratory for the collaboration between France and Japan in the T2K and hypercamiocande experiments. Okay, let me summarize. During the last 50 years, we discovered that neutrinos have small mass and large mixings. IN2P3 has been playing very important roles in neutrino physics and astrophysics, and we expect that IN2P3 will continue to play major roles in physics and astrophysics, and neutrino physics and astrophysics. And let's keep working together and enjoy neutrino physics and astrophysics. Finally, congratulations for IN2P3 50 years. That's all from me. Thank you.
Thank you very much, Professor Kajita. So, are there any comment or question, please? Raise your hand. I can't see you very well. Anyone, anybody wants to? The first one is always the hardest one. Anybody here? I don't see any hand raising here. All right, okay. All right, so thank you again, Professor Kajita. So we move to the next presentation, and Laurent. Okay.
Good evening, everybody. So it's my pleasure to introduce the next speaker. So Andreas Hoecker from CERN. He has historical ties with IN2P3, and he's now the spokesperson of the Atlas experiment at LHC. I'm sure he will tell us very exciting things about the results with smashing particles. I don't know if you will go as far as the intergalactic collider, but okay, please, welcome.
Thank you very much. So I'll try to use this pointer, which, yeah, okay, hopefully this works. So yeah, thank you very much for the invitation. Maybe I hope you will not be too disappointed. I go actually quite a bit back into the past. I think we need to understand the past to get the courage to attack the future, which is significant. I have a few remarks, very quickly, personal remarks. I have a bit more time because I think the previous speakers stopped a bit earlier, so I can take this time. I did my studies of physics at Bonn University in Germany, and I did then my diploma thesis, which we do at the time we did in Germany, at the Opal experiment at CERN. And then I read a few papers on precision tau physics, measurement of polarization, and QCD studies by, for example, François Le Dibérder and Michel Davier and people like this. And I wanted to do my PhD thesis with them, so I embarked to Orsay. And Michel Davier very kindly took me as a student, despite my incapability to explain him why Aleph was so much better than Opal at the time. And then I so I was really very lucky at this place to experience some of the very, very best experimental physicists in the world. And then later through as a member of Babar and the Atlas experiment, I really came to know the bigger French community of physicists, and really I understood how deeply the IN2P3 physicists and also CEA shaped particle physics in the last 50 years. So this is very, very impressive, and it's continuing despite quite significant budget pressure. So it's all made of a handful of particles and forces, and very differently from Democritus, who could just make a Gedanken experiment 2,500 years ago and start, you know, there were millions of atoms who were hooked together by little hooks and they're moving in voids. We had to prove these particles here. We have, you know, after the scientific revolution. And so big experiments were needed, big accelerators and detectors, sophisticated detectors were needed to establish the standard model as it is today and to go beyond. So what was particle physics like in '71? And there's a lot missing. Many of the concepts were already existing, but lots of particles and also the third generation were still not, even the quark picture was not clear, also as Hitoshi told us earlier today. So '71 was an important date because it was the first ever Hadron Collider, which was started. And there was a nice symposium a couple of months ago at CERN. So the intersecting storage ring, as Steve Myers was saying, the almost forgotten Hadron Collider, were operated at proton-proton and proton-antiproton, also ion collider, between '71 and '83. It was about 1 kilometer in circumference, and it reached up to 63 GeV in center of mass energy, and had even the luminosity ratio of a record of Hadron Colliders until 2004. So the idea of colliding head-on instead of using fixed target was really important. If you think of today, the LHC-14 TeV center of mass energy, to do this through fixed target collisions, you would need a 10,000 TeV beam. So that was really an important advancement. And at the beginning, there was foreseen 8 interaction regions, and they were then consecutively filled. And you see here a nice picture. This is the 7th does this work? The 7th interaction region here, which is Peter Jenny and Hans Hoffmann here. If you remember, and there was an impressive control room of the ISR at the time. This was the picture of 50 years ago, so in the early 70s. Oops, sorry. And the ISR, as Ugo Amaldi reminded us, was the first and the only CERN collider which was built without any specific physics goal. And at the time, one knew that protons were not, they had size. So from electric scattering experiment, it was known that it is about 1 femtometer. But it was thought that the proton is kind of a diffuse structure, not really particles inside the proton. And so the idea was that one would do soft proton physics at the ISR. The ISR committee also at that time favored many small experiments, which is very different from what we are doing today. So then, of course, important experiments in the US at the time, SLAC MIT, proved the proton substructure by looking into deep inelastic scattering from electrons, high-energy electrons from the SLAC linear electron accelerator. And then through this magnetic spectrometer, one could see, pretty similar to Rutherford, that there was large angle electron scattering. So there was structure in the protons. And Gargamel was doing the same deep inelastic scattering experiments using neutrinos. And the ratio of the cross-section of the two was 18/5. This tells us that there was fractional charge of these partons, so the quarks. And so the ISR missed the 74 November revolution, and also the bottom quark discovery, although they actually produced J size at bottom, so very beautiful Nobel Prizes missed at CERN. However, the legacy, we shouldn't forget this, enabled the next generation collider experiment. So all these points here, proton stacking, space charge compensation, beam diagnostics, very important, stochastic cooling, I will come back to this, Van der Meer luminosity scans, which are still using today to determine the best luminosity at the LHC, and very important for the experiments, efficient triggers and large angle coverage detectors, and of course jet reconstruction. All this was learned at the ISR. Pierre Dariola wrote, those who worked at the ISR, he says more than here, but tend to see it, and the proton-antiproton colliders, both at CERN and the Tevatron, as a lineage, fathers and son, the success of the latter being indissociable from the achievements of the former. Beautiful words. Of course, Gargamel's breakthrough was the discovery of the neutral current. This one we see, we need, from muon neutrinos you produce electrons. This can only occur through a neutral current. And also particle detectors, not only the machines, also the detectors went really through revolutions in the 60s and 70s, of course, also since then. In the 50s, Jacques de François reminded us in Morillon some time ago, it was really driven by low-rate visuals, so cloud chambers, or high-rate counting experiment like scintillators with PMTs. And then came the spark chambers who allowed to see actually particle tracks with high rates. So already I think of the order of 50 kilohertz. And this was, for example, used also at the Acco storage ring in Orsay in the 60s. Then cylindrical spark chambers were at the heart of the Mark I detector at the Spear ring, which was really an incredible experiment which enabled the 74, the charm discovery, but then also the discovery of Psi-prime, open charm production, tau lepton and quark spin. The development of multi-wire proportional chambers then really launched the electronic detectors of the modern particle physics. Protons were thus made out of quarks, we have learned, and then was QCD right? So we still had to see the gluons, and the gluons were, of course, beautifully shown in these 3-jet events. As we see here, this is a Tasso event display. I wanted to see a cello one, but I didn't find a cello one, so I showed this Tasso one. And this is a 3-jet. So 3-jets in E plus E minus, you produce 2 quarks, and then one quark radiates into a gluon. So you see 3 jets in the detector. And this is really beautiful as evidence for a proof of gluons. In 71 was the approval of a new super collider, super synchrotron, super proton synchrotron. And if you look at the press release here, the price of it was, the price tag was 1.2 billion Swiss francs. And if you correct this for inflation, it's not so different from the price tag of the LHC. And there was a very impressive inauguration party in 77. Then the really important part was this was designed at the beginning as a fixed target, as a synchrotron with fixed target experiments, but then came the idea to make it a collider, which is much better. So antiprotons had to be produced and cooled. And for this, one used the proton synchrotron, produced an average 3.5 GeV protons, and then through 20 hours of stacking and cooling, one could produce a sufficiently dense antiproton stack for transfer into the SPS. And this antiproton cooling was actually an idea using stochastic cooling. So that's a feedback mechanism where you measure the dispersion of the protons, the angular and momentum dispersion, and then you kick them back. And after a long time doing this stochastically, you reduce the dispersion of the beam. And so this was done first at the ICE initial cooling experiment, then at the antiproton accumulator, and then later at the antiproton collector, which allowed then to have a 10-fold improved luminosity for antiprotons. This is very important for the antiproton-proton collider. And the SPP bar S had then also not many experiments, but 2 large-scale experiments, underground areas 1 and 2. You see here the pictures of UA1 on the left with Carlo Rubi and UA2 UA2 on the right. UA1 was a hermetic detector with a drift chamber, calorimeters, large muon system, and a 0.7 Tesla dipole magnet, so that's different from today. UA2 was optimized for W and Z detection in electron channel. No central magnetic field, no muon system, but a high granular projective calorimeter. And then after the significant update also, first silicon vertex pad detector. So that's not on the picture. So both experiments, which I find really impressive, were approved in 87 and first data taking in 89, impossible today. So there is a beautiful picture here. This is the UA2 collaboration meeting with lots of people from IN2P3 on this picture. When I saw this first, I thought that's a working group meeting of some physics group of UA2, but that's really the full collaboration, very different from today. So then, of course, most famously, the WNZ discovery in 83. You see here a beautiful event from UA1, electron and missing transverse momentum, and here a Z candidate with 2 electrons. And after 3 years of data taking, these were the Z candidates from UA1. And after the full data sample, this is the Jacobian, beautiful Jacobian peak to measure the W, the transverse mass of the W, with a really nice measurement from UA2 with 220 MeV uncertainty already. So then this is the famous press conference in 83 where the results were presented for the first time. And Felicitas Paus at the Hadron Collider Symposium made a few comments which I found really remarkable, also still for today. So the lessons learned, the machine background was much less than feared. They were all afraid that maybe the collider wouldn't actually work because of important beam-beam backgrounds. That was not the case. Hermetic detector with magnetic field is essential. Be aware of statistical fluctuation, the tails of distribution. This, of course, for all the people who know, this is the famous monojets and the Altarelli cocktail. And then think carefully about the upgrades. We should do this. And then high granular, this I added, a high granular calorimeter for jet measurement is of course extremely important. And this is an example here, the first dijet discovery at UA2 in 82, a beautiful dijet event you see here. The full sum of the event is 127 GeV, so very strong, clear dijet event. So then the SPP bar S was taken over by the Tevatron, not so much because the Tevatron was bigger. It's 6.3 kilometers, the other one is 6.9, so it's the same size. It's really because of the use of superconducting magnets, allowing them to move to 4.4 Tesla dipole field, so much more than at the SPS. And so then this gave rise to a highest energy, a center of mass energy of almost 2 TeV, and the 2 main detectors here, CDF and D0. So the legacies of Tevatron, very well known, of course, the top mass discovery. We see here a beautiful top mass peak from CDF in 95. And then, of course, also the important Higgs searches. A lot was learned during the Higgs searches at the Tevatron, were used then later for the Higgs discovery also at the LHC. And of course, importantly, this large mass area was excluded, and there was also a hint for low mass Higgs at the Tevatron. In addition, the observation of BS oscillation, which is very fast, very hard to resolve. It was really difficult to do. And high precision top and W mass measurements. The W mass measurement of 16 MeV, the combination of D0 and CDF, is still the best W mass measurement to date. Then came a future circular collider. Visionary people prepared a bright future for particle physics and CERN at the time. A Nobel, you may remember, a Nobel on sabbatical at CERN proposed a very high energy electron-positron collider to study weak interaction, which was followed by a first physics study right away. Several proposals were discussed. The main issue discussed was the circumference of the tunnel. Strong arguments were there in favor of a smaller tunnel to avoid delays and budget overcosts. And these are citations from very famous people. I don't put the names. Reduced size and move out of the Jura and let others build the tunnel. I believe, however, that one should go further and avoid the mountain completely. I would strongly advocate that one takes the fastest and safest solution and remaining on the flat land. So the very wise decision at the time was made to considering the next after project, the very high energy hadron collider. So there was a very complex budget discussions. I was not part of it at all. And there was many compromises made, but the most important part of this was the compromises were there, but the project went on. And so then there were, of course, this was the birth of LEP and LHC, a 26.7 kilometer tunnel facility. The importance, so this was, of course, Bert Richter was the Nobel at CERN on sabbatical. There was this physics study here, then the ECFA lab workshop, and then in 79, and then the famous start of the LHC, the Excel workshop in 84. The lab was formally approved in 81. The tunnel construction really efficient between 83 and 88, and the first beam on the 14th of July in 89. And this is a beautiful picture of the tunnel before the bending magnets went in. It's really nice. And then the first measured Z event was found, they were very lucky, by Opel on 13th of August in 89. So all 4 detectors at lab had implemented the lessons from the earlier experiments, high acceptance and high granularity. High granularity was in particular taken by Delphi and Aleph as a main key feature of their design, allowing the development of particle flow jet algorithms. Silicon vertex detectors for beauty, charm, and tau reconstruction were originally planned already. They came a bit later then. In 1992, all the experiments had vertex detectors. There was a huge amount of experimental theoretical developments. Remember all the theoretical work which was done. This was really the move towards high precision particle physics, which we didn't do before so much. The biggest result, of course, the 3 neutrino families. The top was very heavy, around 175 GeV, exactly where it was found. The Higgs was light. That was very, very important feature also, and was also then driving, of course, the designs of the LHC experiments. But it was not that light. It was heavier than the Z mass, which was really important for supersymmetry at the time. Then there was the extremely precise energy calibration, which allowed to measure the Z mass to 2.1 MeV, which is now a standard candle everywhere. Everybody uses the Z as basically the mass is perfectly known. Lepton universality was tested to the per mil level. This is important to keep in mind when we look at the lepton universality today. And there were deep tests of QCD and tau lepton properties. So I have to show you this fantastic, iconic picture of the Aleph detector with Jacques Lefrançois, Jacques Steinberger, Lorenzo Faure, and Pierre Lesra. Beautiful picture. And despite hints and hopes, a lot of hopes, the Higgs boson was not found at lab and could not have been found. This was it's a very beautiful event, a 4-jet event, which gave rise to a lot of hopes. It was, you see 2 B-jets, so this was a Q-bar BB bar event as Higgs Z production, Higgs to BB bar, but of course ZZ also can produce such type of events. So there were also a lot of physics beyond the energy frontier with a lot of contributions from IN2P3, in particular the asymmetric B factories began data taking at KK and SLAC in 98 and observed CP violation quickly after in the B sector, very pure, fantastic ways to understand CP violation. A highly successful program which is now continued at KEK with the SuperKEK-B project. And there was this beautiful detector which was strongly developed by IN2P3 physicists, the Dirac particle identification system, which was really novel. So you used Cherenkov detectors were already known, but you used the Cherenkov fused silica as a radiator and as a light guide. So the photons would move through reflection into an expansion chamber outside and were measured by photomultipliers. So you see here the expansion chamber and the photomultipliers. A fantastic detector which worked perfectly. And then, of course, here we see the essence of the CP violation measurements done at both Barbar and Bell with this one CP violation, the one phase in the CKM matrix explaining all the effects seen. Now, CP violation in the standard model, as we heard from Hitoshi, is far too small to generate the observed baryon asymmetry. So it's interesting to think about, so what is the purpose of the CP violation in the standard model? So if we had a dial and we could change delta from 60 to 80 degrees or to 40 degrees, what would it change? I have no answer to this. So then there was the penguin lesson. That was really, we were very excited at the time. So this is from, the left plot is from 2004. And you see here, so the main sine to beta measurement was done with these J psi k short, which is tree decay. And then there was these loop decays. And there was the idea, of course, for loop decays, you can have the heavy particles surrounding in the loop. And so this should be more sensitive to new physics. So we had this confrontation of penguin measurements with the sine to beta from charmonium modes. And in 2004, this is the average, the combination of Barbar and Bell was really quite far apart from the sine to beta measurement from charmonium. So we were very excited. And then a few years later, so that's the latest plot, but actually already 3 years later, these points have all moved to the right. It's not that there was a mistake. I don't think there was any mistake. It was just a statistical coincidence and a fluctuation. Happens. There was another important experiment to here also a lot of contribution from IN2P3 here to the theory part more than to the experimental part. This is the high precision measurement of G-2. That was first done at CERN through a series of experiments, and they discovered how one should do this through the magic gamma, removing the uncertainty from the electric field. That was an incredible innovation which allowed them to make very precise measurements, which then continued at BNL and Fermilab currently. And this had to be confronted with the theoretical prediction whose largest uncertainty is hadronic vacuum polarization. And that we cannot predict properly, only at high energy, not at low energy. So we use E plus E minus 2 hadrons data or tau decays. And this was something which was innovated by Michel and friends. And over 25 years, this was improved more and more. And so now the theoretical prediction is in competition with the experimental prediction, which is extremely important. And you see this 4.2 sigma discrepancy in the G-2. And more data at Fermilab is currently analyzed. So we're looking forward to see the results. The Large Hadron Collider. So the 4 experiments, of course, ATLAS, CMS, the large omnipurpose experiments, ALICE, LHC, more dedicated purpose experiment, also very large. The LHC and the experiments are really projects of the superlatives. They have a factor of 7 or 50 larger energy or luminosity, almost twice larger dipole fields, and 16 times narrower bunch spacing than the highest energy experiment at the time, the Tevatron. It used a revolutionary compact 2-in-1 accelerating scheme, which makes it much cheaper to build. The detectors are technological masterpieces. They incorporate all the lessons from the previous experiments and were designed, I think, for the first time, entirely designed and optimized from scratch using detailed simulation. Their physics performance in all cases exceeds the design expectation in really virtually all aspects. Worldwide distributed computing is organized in its own collaboration, and we really, people move their jobs to the grid, don't know where it runs, but it does run. The experimental collaborations count several thousand scientists and span entire careers between proposal and exploitation. A very major ingredient without which we would not be able to exploit the result as we do is the understanding of the proton structure. And this was driven forward hugely by the Hera experiment at DAISY, also with a lot of contributions, in particular to H1 from IN2P3 physicists. The protons, now we know, it's made out of partons, quarks, gluons. And so the cross-section we calculate, which is calculated theoretically, is a convolution of the parton densities and the parton-parton scattering matrix element. And so for this, one needs to know the parton density extremely well. It's so far not possible to predict it from first principles. In future, maybe from lattice QCD, it's possible. So far, it's not. And so one needs to measure it. The best way to measure this is deep inelastic electron hadron scattering, which was done at HESI. And you see here the latest combination of H1 and Zeus. And Zeus, H1 and Zeus combination, which allows then to a very precise prediction of the parton density functions. The run-2 dataset of the LHC, coming back to the LHC, is a fantastic dataset. The overall run dataset is fantastic, but the run-2 is really the best. 13 TeV, center of mass energy, 140 inverse femtobarns of luminosity for ATLAS and CMS. And there's a very good efficiency of the data taking. And if you think about how many particles we have produced in this dataset, 8 million Higgs bosons, 270 million top quarks, 8 billion Z bosons, 26 billion W bosons. If you think of the full data sample of UA2 after the full running was about 2,000 Ws. We're now at 26 billion Ws only after this run. So that is fantastic, and this is really the best data set we have so far for physics, and ATLAS and CMS each produced more than 1,000 papers on this. The Higgs boson, this is a beautiful Higgs candidate event from CMS to 2 photons. This is really the magnus opus of the LHC. The discovery allows us to access a new sector of the standard model Lagrange. In Yukawa couplings, you could call it new forces. Every Yukawa coupling is its own force. Gauge scalar boson interactions, and then, of course, the Higgs potential through a Higgs self-coupling. We see here a beautiful peak. This is what we see in the purest 4-lepton channel, because that's not the only one. The purest 4-lepton channel in CMS, and CMS also acquired now a measurement of the Higgs width, which is very close to the 4.1 MeV, which is predicted by the standard model. And so the width is very low. It's 3 orders of magnitude smaller than the WZ or top width. So that makes us very sensitive to very low couplings, which could couple to the Higgs and be any type of new physics. So it's really very interesting. And it's a beautiful measurement, which is not by looking at this peak width here, but looking at the high off-shell coupling and to determine from this the Higgs width. So the BH mechanism, brood angular Higgs mechanism, is real, and we see this, that it's real by looking at this beautiful plot here of the coupling strengths versus the particle mass, and you see that's just all exactly on the standard model prediction. And if you look at the precision of the couplings obtained already, we are at the several % level already after this, this run 2. That's the first run, full run 2 combination. And even for the rare channels like Higgs to mu, Higgs to Z gamma, we are already at the 30% level. Higgs to invisible, which is a particularly interesting mode to look at, for example, the Higgs decay to dark matter, is constrained to less than 11%. The Higgs sector is directly connected with very profound questions. Hitoshi reminded us of them: naturalness, vacuum stability, energy, and flavor. And the Higgs boson discovery now really allows us to directly study this. And that's a project which is over several decades. And I would, in particular, the measurement of Higgs self-coupling, which requires di-Higgs production, which is 1,000 times smaller cross-section than single Higgs production. That's really hard to measure. A quick remark on this. I think, personally, the discovery of an apparently fundamental scalar particle, we don't know, resulting from spontaneous symmetry breaking, fuels renewed interest in other fundamental pseudoscalars, not only supersymmetry, such as the axion. So we have a new understanding of hadron collider production. There's huge, very similar to LEP, there's huge theoretical progress also in hadron collider physics. You think back, you know, UA2 times, leading order. Then in around the 2000s, there was next to leading order evolution with matching, which is quite complicated. And now we are at the next to leading order evolution. All these predictions now are next to leading order, which is really fantastic. And the observation of numerous very rare channels which are testing the standard models, which have never been seen. Vector boson scattering has never been seen before. And this is an event display of a tri-boson, tri-W production, which was just observed this summer. So this is these famous staircase plots the experiments produce, where you see the cross-section for various processes and many orders of magnitudes in excellent agreement with the standard model prediction. In most cases, next to leading order prediction. And we are going as low as femtobarns here, 4-top production. The 4-top production cross-section is 70,000 times smaller than di-top production. That's where we're getting at. So then, of course, there are deep and broad searches for new physics. We can use these very high mass di-jet events to look for new physics. And this is done, of course, since the beginning of the LHC. For example, looking at the invariant mass of the di-jet production. And this looks at quark substructure. So if there were a substructure, we would see, for example, excited quarks. We would see resonances popping up in the di-jet mass spectrum, which is not seen here in the CMS plot. We can also look for new forces, Z primes and W primes, new symmetries as high energy. And these have not been seen so far by looking at dilepton spectra. Then, of course, we can look for dark matter. Dark matter production, you know, protons, if it couples to dark matter, should be produced. And the protons, the dark matter would just go through the detector and we wouldn't see anything. The only way to see dark matter, and this is an ingenious way, is by looking at additional particles produced and then look at the momentum conservation. And so we would produce, for example, a hard jet event, which would recoil against dark matter. And this is a beautiful dark matter event we see here. We have the proof of dark matter, one would see. Fantastic, nothing on the other side. Of course, the standard model through Z to 2 neutrinos produces exactly the same events. So this is unfortunate, but it does it. So this is background, and what we are looking for then is to look if there is excesses at the high jet momenta, high transverse momenta, versus the Z plus jet backgrounds. And you see so far in these plots, this is measurements from CMS, there are no excesses at these high missing transverse momenta. And this biggest background here is indeed Z plus jet events. So I have one more, which I actually didn't put in, since I have a little bit more time, I would just present this in words. Another very nice measurement is, and Johanna will come back, of course, to heavy ion physics later, but this is particle physics with heavy ions, which is, if you take lead collisions and you don't collide them head-on, but you just ultra-peripherally, so there's actually no strong interaction between the two, but only electromagnetic interaction with quasi-real photons colliding each other. The electromagnetic fields created there is 10 to the 25 meter up to 25 volts per meter. That's far beyond the Schwinger limit. And in this case, photons scatter, and we can measure light by light scattering directly in our detectors. And we have beautiful heavy ion events with nothing in the detector, just two light beams, which were scattered from the initial state. Very beautiful measurement. And this, of course, allows us to measure QED in a very strong regime. So, flavor physics. The successes of the standard model flavor structure is since long a source of discomfort to BSM physics. When I came myself from Barbar, we haven't seen after the penguin disaster, we hadn't seen any new physics. So I think we want to find new physics at the LHC. That's the feeling you get when you work on flavor physics. So there were beautiful measurements. One of the most important measurements done at the LHC, in addition to the Higgs discovery, is this measurement of the BS to mu decay, which is 3 × 10⁻⁹, the branch fraction. Imagine how rare this is and what a beautiful measurement by LHCb here. So then another one, the corresponding for the BS modes for sine to beta is sine to beta s or phi s. For me, that's even more interesting than sine to beta, because in sine to beta, we didn't know the prediction so well. There's quite some uncertainty. You have to do this whole unitarity triangle fit to predict sine to beta. Here, we have a perfect prediction. The angle is very small, but new physics would make it large in any case. So this is a fantastic measurement, and I had a lot of hope here. Currently, all the measurements by all the experiments are in good agreement with the standard model prediction here. And you see the standard model prediction has almost no uncertainty. So that's a measurement we will continue until the very end of the LHC, and it will be very interesting to follow. So sources of the success of the standard model flavor structure is since long a source of discomfort for BSM physics, as are anomalies a source of excitement, of course, the other way around. And these anomalies, as you all know, exist in the B sector. In fact, the most interesting one with respect to theoretical uncertainties, here there are no theoretical uncertainties if you just look at lepton universality. So if you take a B to K star E plus E minus and mu plus mu minus over B K star E plus E minus, and then you even take a double ratio by taking the J psi K star over the non-resonant E plus E minus and mu plus E minus, then you have a double ratio, which makes it then systematically much more interesting. And if you plot this, you find out that it should be 1, but it's actually smaller than 1. For the K star, it is also smaller than 1 for the K. It is also smaller than 1 for the K plus star and for the K short. Here the uncertainties are larger. These are recent LHCb results. So altogether, that's quite interesting, and I hope we will not just find another penguin problem here. The next steps. So this is the grand plan for the LHC. It was just changed into a direction which was necessary. So at the end of this long shutdown 2 here, we will restart data taking. We are all looking very much forward to restarting data taking in next March. So there will be, of course, there will be a beam commissioning period. So the first really high energy stable beam are 15th of June. We will see if this is possible. And then there will be 4 years of data taking for run 3. Then there will be 3 years LS long shutdown 3, with the implementation of the Atlas and CMS. We call this phase 2 upgrades. They prepare for the high luminosity LHC, where we move up to 7 × 10⁻³ in luminosity and 200 of pileup events. And this is a huge challenge. So this will be a Higgs factory. Currently, remember, in run 2, we had about 8 million Higgs bosons. We will have 400 million Higgs bosons. So we will be able to do very precise coupling measurements. We will have access to Higgs self-interactions for the first time, and increase overall rare and new physics sensitivity in all areas, including flavor, of course. With this improved LHC and the injectors, we need these large-scale detector upgrades for improved robustness against pileup and radiation. And in fact, in reality, half of CMS and others are currently working on the upgrades. It's a huge, huge effort. So I wanted to show you also the machine, of course, is working on the upgrade. And this is new galleries, which are produced around 0.1 and 0.5, the 2 interaction regions of Atlas and CMS. There will be service galleries. And this is a picture of the new small wheel, which we just added to Atlas. And you see here the new small wheel is actually 10, so it's 10 meters. It's a small wheel. The big wheel is 25 meters. So the small wheel was lowered through the shaft into the Atlas detector. We were very, very, very happy that this was possible. So the standard model is complete. And Hitoshi Murayama already showed us all the problems we have in the standard model. So I will not repeat any of those. I wanted to make one point which is really made by this beautiful paper here, the 18 arbitrary parameters of the standard model in your everyday life by Bob Kahn. It's a fantastic paper. You should really have a look at it. It shows you how fragile atoms are. If you have a dial, he says, I have a dial, I change parameters. He changes the electron mass towards the muon mass, but even a little bit. He changes the d quark and the u quark. If you make the u quark a bit heavier than the d quark, currently neutrons are 1.3 MeV heavier than protons. If you go the other way around, in each of these cases, you run into disaster. The rich chemistry we have is impossible in these scenarios. If you make the d quark too heavy, again, you will run into stability. We live in a kind of a miracle, one would think. So many deep questions remain, many of which require energy frontier experiments. And there was the scientific priorities for the future were set by the implementation of the recommendations of the 2020 update of the European Strategy of Particle Physics, and I have put them here. Fully exploit the highly massive LHC, build a Higgs factory to further understand this unique particle, again emphasized by Hitoshi Murayama. Investigate the technical and financial feasibility of a future 100 TeV energy frontier collider at CERN, ramp up the relevant R&D and continue supporting other projects around the world. This is a phenomenal machine. So, and I wanted to go through this full history, as I said at the beginning, to give us courage to think this way. It's hard, I know, it's hard. So a high luminosity 100 TeV hadron collider offers huge physics potential. 5 sigma discovery of Q star, excited quarks until 40 TeV, Z primes until 40 TeV, gluinos until 16 TeV, precision probes of Higgs and self-coupling and rare processes. We will have 400 times larger di-Higgs production cross-section at 100 TeV than we have at 14 TeV. So we will really make precision measurements of the Higgs potential with this machine. So this is all given physics. Standard model poses like longitudinal vector bosons. So not only vector boson scattering, what we are currently doing, means longitudinal vector bosons. So the really interesting one for electroweak symmetry breaking will be studied at very high energy, up to 3% with this machine. And then, of course, huge searches for WIMP dark matter, sensitivity between 1 and 3 TeV, and a very big heavy ion program in addition. Now, it's clear the timescale, size, technical challenges, the cost of this facility are daunting to me as well. And can we do it? I have not an answer whether we can do it. So now I have just 2 points I would like to point out. Where LEP and LHC so different? If we think about the timescale, I hear this many times. Oh, 70 years ago. It's 70 years. We have to think through 70 years. That's so long. But if you think back, the moment where the civil engineering started in '83, and the end of the LHC, high luminosity LHC program, this is 57 years. And I don't think anybody, when you started to civil engineer the tunnel, was thinking it would take so long. So we should just, I think we should take this in pieces and not just be overwhelmed by the full thing. So then the plastic Higgs factory gives us the time to develop the high field magnet. This is the biggest challenge required for the new high energy frontier. The R&D must be pursued with full strength and conviction without a realistic hadron collider option. The tunnel facility, I come back to the tunnel facility before, will have a difficult standing. So we need to have the possibility to create the hadron collider after. I believe progress in particle physics crucially relies on an energy frontier experiment. So we've come a long way, and I believe the adventure continues, and I want to congratulate very much IN2P3 again for shaping the field so much and hopefully for shaping the future of the field as well. So thank you very, very much.
Thank you very much, Andreas, for this very enthusiastic journey through the last 50 years and for giving us courage for the next challenges. So thanks a lot. Is there any question in the room? Sorry, is there any question? Comments, remarks? Yeah. Do we have a mic?
Thank you very much. This was a beautiful talk, but what plans are being made for the energy frontier? As you know, the US particle physics community chose to go to the intensity frontier. So is the energy frontier something Europe is pursuing? And what are the plans?
So yes, absolutely. This is very intensely pursued. Also, by the way, there is a lot of support for the energy frontier from the US side. So there is the task from the European strategy upgrade was to make a feasibility study for the machine. And so this is ongoing very intensely at CERN and in the world currently, yes. And there's also, of course, similar processes are ongoing in Japan, in China as well as for a very similar projects. But just to say, the US is enthusiastic about an energy frontier machine.
Questions, comments? I don't see any. Thank you again, Andreas.
So good afternoon, everyone. It is my pleasure to welcome the next speaker, Johanna Stachel, who is a professor at the University of Heidelberg. Johanna has been a spokesperson of the NA45 Ceres experiment and a project leader within the ALICE collaboration. And remarkably enough, she received just 1 week ago the Federal Cross of Merit, which is awarded directly by the President of the German Republic. So we are very honored to have her today to discuss a topic that is of the utmost importance if one wants to understand how the infinitely small and the infinitely large are connected. Thank you, Johanna.
How do I find my talk? How do I find my talk?
It's probably just press return key. No.
It's Stachel here.
Stachel, it is one, yeah.
Is it the first one?
Perfect, yes. Okay. So it's a pleasure to be here. When I was first approached about this talk by Fanny Farget, she asked me to review nuclear physics. And I thought about it, and then I said, I cannot do that. I've done that in the early 90s, but I could not do it today because the field is too large. So I will take you on a journey that is about exploring the phase diagram of strongly interacting matter. And that journey has taken us about the last 35, 38 years. And as you will see, French physicists and French institutions have played a significant role in this. So you see here in the plot the phase diagram of strongly interacting matter, and I will just share some highlights with you, some highly selected topics, physics insights, and in the end, a few comments on the perspectives. I think the questions come from what we have learned already. Now, let's first start at the low energy end of the phase diagram, and that is the region. Sorry, I have to get used to this interesting instrument here. So that is the liquid-gas phase transition. The beginnings really are in the seminal paper by George Birch and Phil Siemens from 1983, where they already linked the liquid-gas phase transition of nuclear matter to a phenomenon that could be observed experimentally, and that is nuclear fragmentation. And in fact, they argued that fragmentation will occur when the nuclear matter has expanded adiabatically to the onset of a hydrodynamic instability, namely the derivative of the pressure with respect to the volume going negative. And that is what is in this plot here called the spinodal region. So we see nuclear matter. Of course, you all know the liquid drop model. And then through this spinodal region, one reaches a gas. And that is the story I will show you. So there was the important measurements by Aladdin where they could show the caloric curve for this liquid gas phase transition. You see here the temperature that is determined from the ratio of helium to lithium isotopes as a function of the excitation energy per nucleon. And there is this rise that follows the behavior that is known from the liquid drop model. And then you see something that looks like a first order phase transition with a latent heat. And then finally the rise that follows exactly a free gas of nucleons. Now, the measurement of the latent heat was an important accomplishment by the joint Indra and Aladdin collaborations. Indra had first worked at Ganil, and then they joined forces and did measurements at GSI in the energy range 60 to 100 MeV per nucleon. And in fact, it was already pointed out by Philippe Chomas and collaborators that bimodality in the fragment charge distribution is a signal for the phase transition. And what you see here is this beautiful measurement of the charge of the heaviest fragment as a function of the excitation energy. And you see here, this peak is the evaporation peak that comes still from the nuclear liquid. And then down here, this is the phenomenon of multifragmentation. And it could be deduced from this plot, one could deduce the latent heat for this first order phase transition from the liquid to gas to about 8 MeV per nucleon. And this is a beautiful paper by Eric Bonnet and collaborators. Now, coming to the high energy part of the nuclear phase diagram, I show you here the equation of state of hot QCD matter. Well, if I come closer, it's very hard to point. Can you really not hear me? I cannot see anybody. Ah, okay. Okay, fine. Okay, so what I show you here is the equation of state of hot QCD matter. Now, the computation of the QCD equation of state was one of the major goals of lattice gauge, of the lattice QCD community since the 1980s. And now we have 40 years later, we really have consolidated results on this equation of state by different groups and extrapolated to the continuum and to the chiral limit. And what you see here is the energy density normalized to the T⁴ rise for a relativistic gas. And you see this rapid increase. And that signals the release of new degrees of freedom in the transition from hadrons to quarks and gluons. And in fact, lattice QCD points to a continuous crossover transition. We will talk more about this. Now, associated with this phase transition is the restoration of chiral symmetry. That is a fundamental of symmetry of QCD that is spontaneously broken in nature. And there is an order parameter for this chiral symmetry restoration, and that is the chiral condensate, or its susceptibility, meaning the derivative with respect to the mass. And this peaks at the critical temperature. And what you see here are computations of this order parameter derivative for different size lattices, and the results for large lattice size converge towards indicating or pseudo-critical temperature for this phase transition of 156.5 MeV, and this is now known with a precision of 1.5 MeV. This was really this 35 to 40 year effort. Now, the experimental program started simultaneously in 1986, both at the HES in Brookhaven and at the SPS at CERN. And then we moved on to the colliders with RIC in the year 2000 and the LHC starting in 2009, or with heavy ion collisions in the year 2010. And you see here a tremendous increase in center of mass energy by 3 orders of magnitude. At all of these facilities, there were a number of large experiments dedicated to studying the phase diagram of strongly interacting matter. Now, I should briefly familiarize you with the space-time evolution of a collision of 2 relativistic nuclei. This is shown here in a Minkowski diagram, and up here you see a sketch of the different phases the system undergoes. So basically, we have 2 gluon sheets colliding, and there's an initial singularity. We have quantum fluctuations in these gluon fields, and the system evolves into an equilibrium state, and that is what we call the quark-gluon plasma on a time scale of a fraction of a Fermi. This plasma lives about 10 Fermi over C, so the time it takes light to fly 10 femtometers, and then it hadronizes, and we observe the debris in our detectors and have to make our conclusions. Now, let's start slowly to look at observations. So the most fundamental thing is just to look at the number of charged particles that are produced, and I show you here the multiplicity of charged particles normalized per colliding nucleon as a function of the collision energy in the center of mass system. And you see here the lower data points. These are proton-proton and proton-nucleus collisions, and the upper points, these are collisions of nuclei. And you see this much larger rise, in particular when we come to the LHC. And what this means is that there is a larger fractional energy loss in a nuclear collision. There is just much more energy deposited in the central region as compared to a proton-proton collision. And that is, of course, associated with what we call the nuclear stopping power. So what you see here is, this is the distribution of protons measured over the full phase space at the HES. And at the HES, nuclei stop each other completely. So we have a distribution that is clearly peaked in the middle, and that means there's a rapidity shift of 1.7 units. Now, going to the SPS, there's already a slight onset of transparency, and the rapidity shift is 2 units. And coming to RIC, there is a beautiful demonstration of the phenomenon called limiting fragmentation. And what you see in this plot down here is, if we shift for different colliding systems all rapidities to the beam rapidity, and then we look going downward in rapidity, and you see here a complete agreement of the proton distribution measured at the SPS and measured at RIC at a 10 times higher center of mass energy. And so that means that also at RIC, and presumably also at higher energies, there's a rapidity shift of 2 units. And what this translates into is that the fraction that is 1 minus e to the minus delta y is the energy that is lost from the beams and that is deposited in the central fireball. And that means 86% of the beam energy. Yeah? While in a proton-proton collision, this was measured at Fermilab in the early 1990s, the fixed target experiments, there's a rapidity shift of just 1 unit, just shy of 1 unit. And that means only 60% of the beam energy is converted into new degrees of freedom. Now, that of course translates into very large initial energy densities. And we can translate using this idea proposed by Kahn many years ago, the transverse energy that is measured in the collision, or also the multiplicity multiplied with the average transverse mass that comes from the measured spectra. We can compute the energy density, and by putting here this Jacobian that relates rapidity and spatial coordinate, we basically say at what time do we measure this energy density, and people typically take here a canonical number of about 1 Fermi. And then what you see going from AGS to SPS to RIC to LHC is that the energy densities in the central region grow from 1.4 GeV per Fermi cubed to about twice that at the SPS, again another factor 2 for RIC, and finally at the LHC at 1 Fermi we are at about 12 GeV per cubic femtometer. And of course this can be translated into a temperature. You all know that energy density grows like the force power of the temperature. So for the AGS we have temperatures of about 170 MeV, SPS 210, at RIC 300, LHC maybe 360. And one could argue that maybe looking at 1 Fermi is conservative, and in fact one should take the inverse of the saturation scale, and then what would rather end at the 10th of a Fermi, and you see immediately the numbers get, of course, much bigger. Now the point here is that all of these temperatures are above the lattice QCD result for the pseudocritical energy density and temperature for the phase transition between normal matter and quark-gluon plasma. Now, let's look next at the hadronization of this hot quark-gluon fireball. And what I show you here is the first measurement of a comprehensive set of hadrons from the Brookhaven AGS, and we had these data at about 1993. And you see there's a large dynamic range here. We have protons and pions that are produced at comparable probabilities. Here we have proton to antiproton at a few times 10 to the minus 4, and then the most extreme measurement was the measurement of deuterons to antiprotons, which is another 5 orders of magnitude suppressed. And in fact, all of these data could be described by a successful application of a statistical approach to hadronization, a grand canonical statistical approach. And there are only 2 fit parameters. There's a temperature and there's a baryochemical potential. And these lines indicate that with these 2 parameters, one can really describe this whole set of data that really cover 9 orders of magnitude without any deviation. Now, later going to higher beam energies, this was extended, and one can again obtain parameters, a temperature and a chemical potential. And what I want to show you here is the evolution going from low energies, AGS to SPS to RIC to the LHC, of various observed hadron abundances. For instance, the proton to pion comes down here, antiproton to pi minus goes up, and the 2 come together at the colliders. The K plus to K minus shows a maximum. The K minus to pi minus just goes up. And the solid lines are just coming from this very simple statistical approach. And you see that it covers even non-monotonic features in the data. Now, coming to the LHC, we have a really beautiful set of measurements from the Alice experiment, hadrons and nuclei, antinuclei, hypernuclei. And what you see here is the colored points. The red points are for particles and for nuclei, and the green points are for the antiparticles or the antinuclei. And first of all, you see that they are produced in equal proportions. The data cover here 9 orders of magnitude, going from pions to helium or anti-helium down here. And the solid blue lines show that there is just one parameter that is characterizing all of these measurements, and that is a temperature. In a statistical approach with a temperature that is now fitted to the data, a temperature of 156.5 MeV with a statistical uncertainty of 1.5 MeV, one can describe not only hadron yields, but also nuclei and even the yields of very fragile objects like hypernuclei or anti-hypernuclei. And if you are interested in that, we can come back in the discussion. Now, the biggest difference at the LHC compared to lower energies is that in fact matter and antimatter are produced in equal proportions at the LHC. And this is consistent with a central region where you have equal numbers of quarks and antiquarks, similar to the early universe. And that means, in a more technical language, that the baryon chemical potential is consistent with 0. Now, taking all of these measurements from the early 90s to today and putting them into a phase diagram where we plot here the temperature and here the baryon chemical potential. These different colored points are the measurements. Down here, there are even measurements from CIS, GSI, then AGS, SPS, RIC, and finally here, the LHC. So looking at this, you see clearly there is a limiting temperature. There is obviously a maximum temperature that hadronic matter can sustain. And this temperature is just shy of 160 MeV if we take all of the data together. And now, of course, we can go back and we can compare this to what we know now from lattice QCD about the phase transition of chiral symmetry restoration. And that is the turquoise line here, and the value for 0 chemical potential is 156.5 plus minus 1.5 MeV. And this exactly agrees with what we measure in the ALICE experiment. So that means hadrochemical yields are frozen in as the system goes from the quark-gluon plasma back to normal hadronic matter. Let me skip this and come to hadron spectra and their correlations. So I show you here a set of spectra measured by the Na49 experiment at the SPS, and what immediately strikes you is that if you compare pions here to protons or to deuterons, the larger the mass, the flatter the spectrum. And this is a plot I remember I prepared for the International Nuclear Physics Conference here in Paris in 1999. And what you see is that if you look at the slope constant that is characterizing these spectra, then the larger the mass, the larger the slope constant. And this is a behavior that is very characteristic for a system that undergoes strong collective expansion. Now we know that really hydrodynamics can describe this behavior, and I will come to this. So we have a superposition in the spectrum of random thermal motion characterized by the temperature and this ordered collective motion that, of course, imparts a larger momentum to more massive particles. And what one finds is that the expansion velocity is about half the velocity of light, and the temperature that one finds here is about 127 MeV. Now, I should say this is the temperature at which elastic collision cease, and this is what we call kinetic freeze-out. So that means after the system hadronizes, it still hangs together for a little while, a few Fermi over C, and then interactions, also elastic collisions, stop. Now, going to the LHC, to RIC and the LHC, this phenomenon becomes even much more dramatic. And you see here spectra of pions, kaons, and protons. The black points are for RIC, and the colorful points are measurements from ALICE. And you see very dramatically that the protons are shifted out to large transverse momentum and have a very flat spectrum. And this is very well described by three-dimensional relativistic hydrodynamics and models, for instance, here the EPOS model by Klaus Werner and his colleagues from Subatec is plotted here together with the data and captures this very well. And the expansion velocity here at the surface of the fireball is 3/4 the speed of light. Now, there is another consequence associated with this, and this is if we go away from central head-on collisions to collisions where the overlap of the two nuclei is only partial. I look now here in direction of one of the two beams, then initially we have a strong spatial anisotropy, and that leads to a different pressure gradient in the reaction plane and perpendicular to the reaction plane, and this leads to a larger collective expansion in the plane as compared to out of the plane. And this can be characterized by doing a Fourier decomposition of the spectral distribution with respect to the angle relative to the reaction plane. And there are these Fourier coefficients that characterize this. I should say, and I could elaborate more on this in the discussion, these coefficients are really the equivalent of the power spectrum of the cosmic microwave radiation. And in particular, I want to show you this V2 coefficient in one slide, and that is what is also called elliptic flow. This is the quadrupole moment of the measured distributions. Now, this shows how this quadrupole component evolves from very low energies, these are MSU and Ganil energies, to cis energies, then going to the AGS, and finally to the colliders. And if the pressure gradient dominates, then the sign of this coefficient should be positive. And it was first discovered in the E877 experiment in 1993 as a tiny 2% effect. But this was the first definitely positive measurement. This was when I did this together with my graduate student at the time, we were very much inspired by a paper by Jean-Yves Olitreau about the anisotropy as a signature of transverse collective flow. This is a paper that has by now some, I think, nearly 1,500 citations. Going to SPS, top SPS energy, this is already much more pronounced, now shown as a function of the transverse momentum of the particles. And this is the first time that this could be modeled with ideal relativistic hydrodynamics and comes close to the experimental data. Coming to RIC, this is where the paradigm arose of the quark-gluon plasma as a nearly ideal liquid. And what you see here is the data points. The black points are beautiful measurements by the STAR collaboration. And the green line is ideal non-viscous hydrodynamics. And you see that there's a small deviation. And in fact, the data require a small ratio of shear viscosity to entropy density to be fully and quantitatively described. Now, people discovered quickly that this hydrodynamic regime is driven by both the initial condition as you initialize the hydrodynamics and the properties of the liquid, such as the shear viscosity to entropy density, and that in fact there's an ambiguity between the two. However, it was pointed out, I think this was one of the first papers where this was shown by Olitreau and collaborators, that this ambiguity can be resolved if you correlate more observables. And for instance, if you correlate the second and the third Fourier coefficient, then you see that only one scenario in this case survives. And this is really a first determination of both the initial condition and of the shear viscosity to entropy density ratio. Now, we have come a long way, and in fact, again, it was a paper by a French collaboration, Nicolas Borghini Dean and Olitro, who pointed out in a really visionary paper that has been guiding the way for many years, that much higher precision can be obtained if we go from these simple Fourier coefficients to cumulants defined in terms of multi-particle azimuthal correlations. And I show you here the latest example from the LHC, where a global Bayesian analysis was done of such new collective flow observables, inlet-led collisions, fitting the data from the Alice collaboration. And what you see here is that they could determine now the temperature dependence, not only the value, but even the temperature dependence of the shear viscosity to entropy density ratio for the quark-gluon plasma. And it starts near the conjectured bound, lower bound for causal field theories, for instance, for this ADS to CFT theory, and then a slow rise with temperature, and also the bulk viscosity over entropy density could be determined, and in fact it peaks just above the pseudocritical temperature. Now, turning to a completely different phenomenon that goes under the name of jet quenching, the question is, at LHC, initially it is all about hard scattering. It is about jets and mini jets. And the question is, how do hard partons thermalize in the plasma? How do they lose energy? And this was first measured in terms of looking at leading particles as a function of the transverse momentum. And the variable that is plotted here is the spectrum in a nuclear collision divided by the spectrum in a proton-proton collision suitably normalized. And what you see here is that at RIC, for the first time, there was a severe depletion encountered, and going to the LHC, these are the black and colored points here, you see that this effect is even stronger. There's about an order of magnitude a difference in the range of 5 to 10 GeV. And going to identified jets, these are measurements here from the Atlas collaboration, you see that even going out to 1 TeV, this phenomenon survives. So this suppression we want to understand in terms of, quantitatively in terms of the energy loss of partons in the quark-gluon plasma. And the paper that was really leading the way here is a collaboration between Bielefeld, Bayer, and French colleagues Yuri Dokschitzer, Peignet, Dominique Schiff, and Al Müller from Columbia University, well before the start of the Collider program in 1997. And they pointed out that in a certain kinematic regime, the energy loss per unit path length is given by the density of color charge carriers and the transverse momentum kicks they undergo in the medium, and that this could even be proportional to the path length. So the energy loss would then go quadratically with the length, and that has to do with the fact how the gluons that are emitted decohere. Now, what I want to show you here is, so what is in front of the path length here, this is what is called the transport coefficient. And this transport coefficient characterizes how the quarks and gluons lose energy. And this is the determination of the transport coefficient as a function of temperature, taking together the data from RIC and from the LHC. And in a rather sophisticated modeling that combines the splitting of high virtuality partons and then later the scattering between jet partons and the thermal quark-gluon plasma once they have fallen below some critical momentum. And what you see is that this transport parameter is now determined, for instance, if we take a temperature of 400 MeV, to have a value of about 0.7 GeV squared per Fermi. So to set the scale one can determine this for cold nuclear matter from deep inelastic scattering data, and what is found for the hot quark-gluon matter is hugely increased. It's a factor 20 to 40 larger. So that means the plasma very effectively slows down partons. Now, the last probe I want to come to finally has something to do with confinement. I told you we know about the chiral phase transition. We can measure the temperature. We can start to measure properties of the quark-gluon plasma. But what do we know about deconfinement? And again, here, the French community has played a significant role in the measurements. Now, the original idea by Matsui and Satz 35 years ago by now was to implant charmonia in the quark-gluon plasma and observe their modification in an effect that is the analog of debye screening in a colored medium, and that debye screening should lead to suppressed production in nuclear collisions. So the first measurements were done by Na38 already at the SPS when there were only light beams, oxygen and sulfur beams, and immediately they saw a suppression. And everybody was at the time very happy and declared victory. But then I remember the Quark Matter Conference of 1991 in Gatlinburg, where it really dropped like a bombshell when there was the talk by Claudie Cherchel, who with her, in collaboration with Jörg Hüfner, had found that in fact, not only these data, the oxygen and sulfur-induced collisions, but also data on photon and hadron-induced collisions could be described by nuclear absorption. So the charmonium dissociated by cold nuclear matter with a cross-section of a few millibarn. This cross-section was then measured more precisely by Na38 and the successor experiment Na50 to be 4.3 plus minus 0.5 millibarn. And then finally, looking at central lead-lead collisions, there was a significant deviation. So the line I show you here, this is the normal suppression on cold nuclear matter. And here for central lead-lead collisions, you see a significant suppression, and the definitive paper in quantifying these data was by Jean-Paul Blaiseau, Dean and Olitro, who could describe this by the dissolution of charmonia at a critical density of 3.7 particles per cubic femtometer. So when the density is higher, charmonia are dissolved, and in order to get this last downturn of the data, they also had to include energy density fluctuations, which they modeled in a beautiful way. Now, that was the year 2000, and about at that same time came a new insight, and that is the quark-gluon plasma may well screen all charmonia, but the charm quarks remain in the system. They remain in the fireball, and eventually they have to hadronize. And maybe they hadronize in the same way as the light quarks and the gluons at the phase boundary. And thinking this to the end, it is clear that at the colliders we have to come into a new regime, because more and more charm is produced. And so eventually there should be enhanced production at the colliders, and this would be a clear signal of deconfined charm quarks in the plasma. Now, when we first proposed this in 2000, we really had to take cover, because the people thought this was a pretty ridiculous idea, and it was only in physics letters with Jean-Paul Blaiseau as an editor that this could be published. Now, how is this done technically? We have to, of course, know how many charm quarks are in the system, and we know they're all produced in initial hard scattering. Thermal production in the plasma is really negligible. And so the number of directly produced CC bar pairs comes from data from the measured total charm cross-section, and this can also be computed in perturbative QCD. For the hadronization at the critical temperature, we can follow the same statistical approach as we use for hadrons with light valence quarks. And technically, this is implemented by a balance equation that relates the number of directly produced charm quarks measured by the charm cross-section to the thermal densities for singly or doubly charmed hadrons. And there's a factor in between that makes this an equation, an equality. That is a so-called fugacity, but this is not a free parameter. Yeah, this is fixed by the charm cross-section that is measured. And for instance, at full energy LHC, this factor for lead-lead collision is 30. And you will see the significance in a minute. Now, coming to RIC, at that time RIC was starting, and of course charmonia were measured, and there was a big disappointment. This is from the Phoenix talk at Quark Matter in 2006, and they remarked that the suppression pattern at the SPS and at RIC, although there is this large increase in energy density, is the same. So you compare the red and the black points, these are comparable kinematical regions, and you find the suppression at RIC and SPS is the same. So is this either a conspiracy that the cold matter suppression is larger at the SPS and the hot matter suppression by the plasma is larger at RIC? But it would really be odd if these two completely balance. Or is there already a strong effect of recombination of charm quarks that are deconfined into charmonia? And the speaker ended his talk with, how could we get so lucky? We do everything beautiful collider, and then we measure the same suppression as we have seen already at the SPS. Now, I should say that these data could already be well described by using this statistical hadronization approach also for charm quarks. Now comes the LHC, and the expectations were captured in this article by Louis Kluberg and Helmut Satz, saying that either we finally see the thermal dissociation and the yield practically goes to 0, a few percent because of the nuclear corona, or something dramatic should be happening. So RIC would be sitting here where the two give the same prediction, but going to the LHC, we must see a difference. And the difference we see. Yeah? The blue data are now the J-psi at RIC, at forward rapidity and at mid rapidity. Again, the spectrum normalized to proton-proton collisions, and the red points are the Alice points measured at the LHC. And you see there's clearly a huge increase. Although the energy density is much larger, J-psis are not suppressed, but they are increased, and they're even stronger increase at central rapidity where the energy density is largest. So looking at the picture, I think the answer is clear. Now, let me capture this in just one slide, going back to what I showed you in the beginning. Namely, this is the spectrum of hadrons and nuclei with light valence quarks. And then we put in the same plot the J-psi. And it sits up here lonely about 3 orders of magnitude above mass 3 nuclei. So there's an enhancement of a factor 900. And this factor 900 is really just this fugacity squared that takes all of the initially produced charm quarks and distributes them in a statistical fashion over hadrons. And that is, of course, the precondition for this is that we have deconfined and thermalized charm quarks. Let me skip this because I think the time is pretty much up and come to an outlook and an incomplete but maybe realistic wish list for the coming decade. You saw already in the talk by Andreas that we are at the eve of starting 1.3 at the LHC with significantly upgraded experiments and with beam intensities that for lead-lead collisions will reach 50 kilohertz. And so we can really dream of new things being possible. Also, the experiment have undergone significant upgrades to deal with the 50 kilohertz lead-lead collisions. So the open charm cross-section down to 0 PT to have really a solid baseline for all charmonium measurements. Measure higher charmonium states in order to determine the temperature for the deconfinement transition. This is not even very well known in lattice QCD, although everything points to the temperature being the same as for the chiral phase transition, but we must determine this experimentally. A big question I didn't talk about at all is to what degree does beauty thermalize in the quark-gluon plasma to have a baseline for the understanding of epsilon production. Direct photons, I didn't talk about them for lack of time, real and virtual, and their azimuthal asymmetries are very interesting probes that directly show the temperature evolution of the quark-gluon plasma. Low mass dileptons, and here I mean dileptons really in the range of the rho omega phi and below, are the only axis I think we have to directly look at restoration of chiral symmetry. Fluctuations of conserved charges in a limited phase space region, these do fluctuate, should allow us at the LHC, because we are close to the chiral limit, to probe what criticality the chiral phase transition is. In lattice QCD, it looks like this is 0.4, and the question is, can we learn about the criticality of the chiral phase transition from experimental data? And we think that in a very difficult measurement of 6-order cumulants of net charge fluctuations, we can do this. And of course, at lower energies, there is a great interest, and this will also be addressed by the upcoming facility at FAIR, to see a critical endpoint in the phase diagram where a line of first-order phase transition ends. And there are of course, also tasks for theory, and the list is in reality much longer. So I think we are really looking ahead to another probably 2 decades or so of exploring this physics at the LHC with greater and greater access and understanding to the phase diagram of nuclear matter. And with this, I like to end, and thank you for your attention.
Yeah. Thank you very much, Johanna. Are there some questions in the audience? I don't see. It was very clear. What is, to your opinion, the most difficult challenge to overcome to answer these questions you feel? Is it?
What is the most difficult challenge? I think to get enough precision at low momentum. All of these quantities, if you want to, I mean, it's the opposite of what the direction Atlas and CMS are going into, looking for new physics beyond the standard model. If you want to probe the quark-gluon plasma, you have to be extremely good in the soft sector. And so we have to measure soft photons, we have to measure soft lepton pairs, we have to measure charm the yields of all charmed hadrons and of beauty hadrons down to 0 PTE. And this requires experiments running at high rate, no trigger possible, and it requires superb vertexing. So I think it's detector it requires particle identification, and these are the experimental difficulties. And that is what sets our optimization apart from how CMS and Atlas are optimized, for instance.
Yes, there is one question.
So, Johanna, thanks a lot for this beautiful talk. So, if my understanding is correct, deep in the QGP, big quarks and C quarks have a modified mass because the temperature is different. Is there any hope one day to have a direct probe of this modified mass of the heavy quark deep inside the QGP?
I hope. I think this goes with my theoretical wish list to determination on the experimental side of temperature-dependent transport coefficients, and they are different, you know, of course, very well. There are different transport coefficients, and the question is how are they related by the dissipation fluctuation theorem? And if one has, at the same time, very good theoretical calculations, I think we can get access to something like effective masses that are, of course, characterizing strongly interacting regimes. And so my hope would be, yes, we get there, but we need precise measurements of many different parameters, and we need at the same time a committed theoretical effort such as you are undertaking it and other groups around the world. So this is, I think this is extremely difficult, but why not? Right? This is, after all, the same phenomena that characterize condensed matter physics are also characteristic of QCD in the strongly interacting regime. We know now the quark-gluon plasma is not an ideal gas, but it is a strongly coupled medium, and therefore effective masses play an important role.
Thank you. I don't see any other question, so I think we thank you again. And we have now the coffee break for 30 minutes, so we will be back at 5:10. Please, ladies and gentlemen, we are back to the symposium. Yes, we will have time to discuss after the talks, but let's remain on time. So we shall continue the symposium with the next speaker, who is Annie Aprahamian. Annie is a chair professor at the University of Notre Dame. And she is one of the 5 vice presidents of the International Union of Pure and Applied Physics, of which the main president is Michel Spiro. And Annie is also chair of the Scientific Council of EFRIB, and she's present or chairing many different councils in Europe. And in addition, she's been recently having the responsibility of the direction of the Ali Kanyan Research Laboratory in Armenia for launching a new cyclotron for the production of radioisotopes for nuclear medicine. So she's using her skills in nuclear science for the benefit of society. And for the benefit of our symposium, she will discuss the evolution of baryonic matter over a period that is much longer than our 50 years of existence. So thank you, Annie, please.
Thank you very much, Fanny. Good afternoon. Bonjour. I'm supremely delighted to be here with all of you for this celebration of the 50th anniversary of IN2P3. 50 years of scientific discoveries that have all gone to explain our place in the universe. Andreas earlier mentioned how we live in this wonderful conditions in just the right place in the universe. That is in fact true. So I would like to congratulate all of you, actually congratulate all of us as well. So congratulations on the 50th anniversary. My talk is going to focus on the evolution of baryonic matter. So you will see me escaping back into the framework. The emphasis here is really what we know and what the open questions are. So often I will make the overall outline on what we know and then lead with some of the conjectures of what we don't know and what the open questions are. So if we look, the first speaker in the symposium today showed already this plot. It is the energy distribution of the cosmos, and you see that baryonic matter is less than 5% of the energy distribution. That 5%, however, is responsible for life. It's responsible for the chemical element abundances that we see in our universe. That's a pretty important 5%, or less than 5%. It's the visible universe in which we operate. I will give a very brief summary of what the issues are in nuclear astrophysics. We can think of nuclear astrophysics as the main engine of the universe. So nuclear physics operates over a broad range of astrophysical conditions and scenarios. It operates under the restrictions of nuclear physics. It follows the rules for nuclear structure, nuclear reactions, and then takes advantage of all the messengers. So I haven't listed the messengers per se, but the detectors. I've listed the gravitational wave detectors, Virgo and LIGO, that gave us a lot of information, and the electromagnetic signatures that we see. And I have listed neutrinos, even though they have nothing to do with baryons. So if we take a look at the entire history of our universe from the Big Bang to the present, we can basically separate what we expect for the elemental distributions in the Big Bang. For example, we think the primordial elements are only hydrogen, helium, and lithium. We understand that the oldest stars, sorry about this, I keep moving ahead. The oldest stars, we know, undergo fusion reactions, and some of the most beneficial energies are up to about iron or so. These plots in the bottom of this slide basically show the relative abundances as a function of the mass number. And we know that the present-day solar system abundances, which basically intertwine the entire history of the cosmos with the nuclear physics, and we see the abundances that we have. We know a few things. We know that to get these very rich solar system abundances, we need neutrons. And we know that to have the fusion reactions in the very oldest stars, we need to have seeds for those reactions to take place. What we don't know are how are the primordial elements going through nucleosynthesis to provide the seeds for those stars. And what we don't know are what are the sources of the neutrons that are enabling some of these neutron-induced reactions to produce the heavy isotopes beyond iron. So the time frame on top is also important, as we see here. Roughly the newest, the first generation stars are not born until after 400 million years. But why did I say 3 minutes to the present? If we think about how does the synthesis, nucleosynthesis take place in the very first generation stars with primordial elements. The figure on the right here shows that effect, basically. This is as a function of time and mass fraction. So my fingers are too fat to be pressing these buttons. So if we take a look at what's available between 0 and Big Bang and the first second, we can see that it's mostly hydrogen and neutrons, and some out of the quark-gluon matter, quark-gluon plasma, you have some deuterium made, but they keep breaking down. The temperature is too high, and you don't have nuclei holding together until much later. That's where the expansion has cooled enough the universe so that deuterium can stay. And we can see that here with the continued existence of deuterium and helium and so on. So basically, that's where you can start for the creation of baryonic matter. What about the lithium problem? So people thought that the interstellar medium lithium abundance should be the abundance that's unaffected by any processes, and that the lithium in old stars would be affected by various processes. So that's called the lithium anomaly. But here on the left are some possibilities of how you can basically bypass that A = 5 and A = 8 gaps, and lithium can be engaged in all of those processes. The emergence of the very first stars I mentioned are probably after 400 million years, and none of those stars have survived till now. They were thought to be rather humongous stars, something like 1,000 times solar masses or actually 100 to 1,000 times solar masses, and not surviving for very long. So this figure shows the comparison with the first generation emergence of first generation stars against our sun here. What are the main questions here? So the two aspects that are important for us to address are basically, how do you start with the primordial element and make those seeds for life? How do you make carbon and oxygen? We always thought that the carbon and oxygen had to be made in later generation stars. But actually, if you look at the spectra of some old stars, you already see that there is some sizable carbon and oxygen in existence there before you have the launching of a CNO cycle. And the other second question is the formation of the heavier elements, basically elements beyond iron, and identifying where are those neutrons coming from. So, a few words about what those first generation star conditions are. I mentioned that they're massive. I mentioned that they're made of primordial material, but they have no CNO reactions, so they're not producing enough energy to fight against gravitational forces. So basically, it's proton-proton reactions, which are quite slow, and the stars are collapsing under their own gravitational pull at some point and releasing material into forms of supernovae. But when is it making carbon? So this figure on the below here shows the energy generation as a function of temperature for proton-proton reactions versus the CNO. We know that the CNO cycle makes much more energy than the proton-proton chain. So where is it that these first generation stars are making that carbon and that oxygen? I already mentioned that there is no stabilization of the star because of the fact that there is no CNO cycle. But there are lots of ways. So these are conjectures of how it might be that you can bypass those mass 5 and mass 8 gaps. And they're basically through alpha clusters. So clustering is a very important effect in this very first generation stars. And I list here 3 possible ways that that could be happening. It could be happening through deuterons as a catalyst and through beryllium-7 and so on. So if we take a look, and I don't expect you to follow the details in this plots here, but there are ways that you can use the lithium and the alphas that are produced in these first generation stars and create enough carbon and create enough oxygen. So there are some ways to bypass, and it involves lithium. So this might also help explain some of the lithium anomaly that's been observed. What is the process? The process is basically using nuclear stepping stones and cluster reactions. Again, I'm not going to go through the details, but you can see you're starting out with deuterium, which only exists after the cosmos has cooled enough, so below 2 MeV. And so deuterium alpha reactions and so on to make the nitrogen, to make the carbon that you can have for the seeds of the CNO cycle. So alpha cluster reactions near the alpha threshold, these are all reaction cross-sections that are not measured well, but this is just an idea of how you could be building up the carbon and the oxygen that is seen in these very early stars. So the process by which it's doing, I already mentioned that there is no CNO cycle. So what's happening is once the star is stopped burning protons, it starts to collapse on itself. It's a process of convection. And that collapse actually creates the conditions in which you can make carbon and oxygen. So I have a slide here that shows some of the simulations of what happens in such a star. You can think of the two color scheme here. The orange is basically material that is flowing out of the star, and the blue is the material that's flowing into the star. This simulation is prepared by Falk-Herwig, and these are the conditions under which you produce enough carbon and oxygen to be the seeds for the next set of reactions to take place for stars. Here is proof that this is the scheme, the spectroscopy of an early star. So early star here is not first generation, possibly second or third generation. And you see that there is already some carbon and some oxygen before you have any sort of onsetting of CNO. So you have the seeds from this primordial material in the first generation stars, which have disappeared, that provide the nucleosynthesis seeds for the next generation, for the early stars, and the material that is formed beyond the initial all the way to the iron region, from what we see in older stars. I have just included the carbon-oxygen figure here just to show this is the holy grail of nuclear astrophysics. But there's different ways that the nitrogen is produced, and that becomes nitrogen-14, and the carbon-12 alpha-gamma makes enough oxygen-16. And basically, it's the ratio of carbon-12 to oxygen-16 that determines what happens in the star, funny enough. So this important seeds being in place are what allows the earlier stars to do all the fusion reactions that make the elements up to about iron or so. Of course, that's carbon and nitrogen and oxygen are not enough. But once you have the CNO cycle, you have enough energy being produced. And then you have to think about processes that you can break out of that CNO cycle and make the other heavier elements. Basically, it's a step-by-step process that you get out of. You make carbon, nitrogen, and oxygen, and then you make all the cluster reactions that you can lead ahead. And of course, you can make even very heavy clusters like carbon-12, carbon-12 that explain some of the abundances of the neon, the magnesium, and the silicon that are heavier. So the idea is that the seeds for such a reaction are being done in this very highly convective environment that normally would not allow, it doesn't have enough energy for it to be a CNO kind of star. But the collapse of the star at the end with the convective processes is really what creates the initial seeds that can go on with further processing. So this figure here, the Hertzsprung-Russell diagram, which is a figure of temperature versus density, it shows the various burning processes. So you see that hydrogen burning is lower energy versus helium burning and carbon burning and so on. It's very interesting that it's these low energy nuclear reactions that specifically determine stellar evolution. The figure on the right here, I've just included it because I find it beautiful. It's the neutrino spectrum for exactly the same processes that are shown here. It's the first time that we actually have a neutrino spectrum of the Hertzsprung-Russell diagram showing all the reactions. So while neutrinos have nothing to do with baryons, I find it intriguing that we can have such a clear picture. Second question is, where do the neutrons come from? So we know from nuclear physics that we need neutrons, and we need abundances of neutrons to make the elements heavier than iron. So where do they come from? There's, of course, the obvious that we find it obvious now, the merging neutron stars for the R process. There's supernova events. And of course, there's the low energy nuclear reactions that release neutrons. So some of the alpha capture reactions on some of the carbon, nitrogen, oxygen actually release neutrons. So we have an abundance of neutrons depending on what astrophysical scenario we're talking about to carry on the neutron capture processes. Here is an example. It shows cross-section as a function of alpha particle energy. And while the details are not important, these are all alpha cluster reactions. So alpha reactions on some of the nuclei that are produced. You see what's interesting here is that they all release neutrons. So for example, carbon-13, it's a reaction with alphas, releases nitrogen, releases neutrons for oxygen, and beryllium-10, so on. You see all of them release neutrons. What is the impact of those released neutrons on the chemical evolution of the universe that we see? Here I have shown two simulations. With regards to where do the neutrons come from, or rather the big question of the decade has been, what is the site of the R process? We have known that you can have a slow neutron capture process and a fast neutron capture process. So the big question has been, where is the site of that R process? We knew it had to be rapid capture in order to get the abundances that we would like. So what's shown here are actually two simulations. One of them is for supernovae. Basically, the two most popular contenders for the site of an R process were supernovae and neutron star mergers. So with supernovae, this distribution in the chart of nuclides is indicated here in color, and below it is the mass fraction as a function of the mass number. You see that in supernovae, while this was a very popular site for the R process, it was clear that neutrons run out before you make anything in the rare earth region. So this is as a function of mass here. You see that you don't make it to the rare earth region in the chart of nuclides. What about the merger picture? Well, the merger picture has enough neutrons to, this is, the blue dots are the abundance distributions, solar abundance distributions. We see that it fits very well some of the heavier, so we're talking about mass 100 to the actinides. It has enough neutrons to do that neutron capture. It's shown here on the chart of nuclides above, and even in this sort of filled-in chart that there's quite a bit of production of heavy nuclei there. The problem was always that we didn't think there were enough neutron star mergers to account for the solar abundances that we observe. Supernovae seemed quite popular, but we didn't know how to resolve the situation that you ran out of neutrons before you got to mass 150, 160 and heavier. Here are some other abundances from nuclei that are above iron. that are produced in different processes. This is in the mass number 30 to 90 range. The blue lines here are the R process abundances, R process simulation, with the black dots are data. And the red lines here are the S process only. S process is thought to occur closer to the line of stability. And then if we also look at carbon-enhanced metal poor stars, there's also an intermediate, it seems like an intermediate neutron process that makes nuclei that are in the strontium and zirconium region. That's about atomic number 40. And some in the mass 130 and even in the rare earth region of erbium and dysprosium and so on. So the question is, where are these other processes taking place? Before the observation of gravitational waves in 2017 from a two-neutron star merger, a group of us were trying to use nuclear properties. As I mentioned, the solar chemical abundance distribution had intertwined with it the history of the universe and the nuclear physics involved. So we thought, can we use the nuclear physics to disentangle what is the astrophysics that has caused these abundances? And the work I'm not going to talk about in great detail. This was motivated by the fact that globally all these radioactive ion beam facilities were coming online. All of the facilities had promised that we will be able to say something about where the site of the R process is. So the question was, what should all these facilities be measuring? Should they be measuring all, or should they be, were there some nuclei that were more important to measure than others? So that was an effort that we made with the black line here is the effort production line. We looked at a number of facilities, so RIKEN in Japan and Triumph in Canada and so on. And we determined the nuclei that were the most important to determine for getting a better handle on the R process. And we made these tables available. Some of these were published in 2016. One of the issues we worried about was the uncertainties associated with nuclear measurements. I've only used this figure here. I could have picked any number of nuclear masses here. I've just picked 3. And these are simulations that show the solar abundances in black and the uncertainties that you would get from the various mass models. You see that the colors, the lighter colors are fairly broad. We said, what would happen if we could make these measurements more precisely? What if we could reduce the uncertainties? Would that allow us to get a better handle at using nuclear properties to understand the inherent nuclear physics? This paper, published in 2016, actually showed that, yes, you can actually tell the difference between the different models. So these are, the red line here is a hot supernova type scenario. And the green line here is what you would get for nuclear properties. These are mass differences. The details are not important. But the mass differences you would get if you had a merger, a two-neutron star merger as the scenario for the R process that produced these very neutron-rich nuclei. This is as a function of neutron number. The issue was that we didn't have data that far out. But we thought if we did have the data, we could certainly distinguish which site was producing the elemental distributions that we see for the R process, and therefore the entire neutron-rich nuclei above iron. So this involved quite a big experimental effort, both at Argonne National Laboratory using a Penning trap and at Uvascula Laboratory. In both cases, attempts were made to measure masses with high precision in traps from fission of uranium-235 to be able to get as far as neutron-rich as possible before the radioactive ion beam facilities came online. The big race was, could we use those nuclear physics properties to distinguish clearly where is the site of the R process? Many of you know the rest of the story. So August 2017, the detection of gravitational waves by both Virgo and LIGO and 70 electromagnetic transients showed that two-neutron star merger is a site for the R process. I mentioned here another two-neutron star merger, which was made in GW 190425. This was also, as I mentioned, two-neutron star merger, but the remarkable thing about the 2017 event was that it had these electromagnetic transients that luckily could record all the data that were associated with the gravitational waves. This is a figure on the left of the color scheme. So the electromagnetic transients were in the visible. Basically right away, as soon as the gravitational waves were detected, there was basically a blue glow coming from the production of the very light elements. And within about 3 days, that blue glow became reddish. And the reddish persisted for about 2 weeks or so. So it was clear from the visible data, you could tell which nuclei were being made in that two-neutron star merger event. If we split up the signals, and that's what's shown here in this Astrophysics Journal Letters paper, which was published right away, you could see that the wave functions were changing of the light that could be seen as a function of time. What this meant is that as it succumbed to the red region, it eventually went to the infrared. So infrared, you could see visible light up to about lutetium and this chart of nuclides, and you could see no further because the signal was in the infrared. NASA is intending to launch a telescope to be able to detect things in the infrared, which are due to the high density of the atomic orbitals and the heavier nuclei, but it has not yet been launched. And also, we got definitive proof from this 2017 event that you were making all these elements up to about lutetium. So that's in the rare earth region, so about 160, which is well beyond where supernova simulations were synthesizing nuclei. So that gave a lot of excitement about, yes, the two-neutron star merger is a site for the rapid neutron capture process. The question remains, did it go all the way to the actinides? Did it go beyond the rare earth region where it went into the infrared and we have no more signal? We don't know. Above in this figure, there's a simulation for a merger scenario in 1 second after the event. And you can see that that lighter blue line actually goes all the way to about mass 290 or so. So that's well into the actinide region, which you see here marked the thorium and the uranium. And right away, in 8 seconds is this darker blue line. And then the black line is within a year. So all of that stuff, if it's being produced, at least in the simulations, it's decaying away right away. Now the simulations have input of nuclei up to about Z, a proton number of 110, and we're producing, the simulation produces nuclei up to about A of 290. If these actinides are being made, is there some other way to get a signature, a direct signature that, in fact, you did make? I mean, many of the astrophysicists feel that once you have populated nuclei in this particular range, mass number 160, 170, it almost had to make the actinides. But the direct evidence doesn't yet exist, and the question is, does it? Of course, if it does get up to the actinides, the question then is, how does it decay away? And fission, we know, while fission has been studied very well for over 80 years, we know that it varies depending on the situation and the circumstances. There has been quite a bit of conjecture by various theorists. Stefan Gorielli has said that fission distributions have to be very different when you get to very neutron-rich nuclei. This is a calculation by Vitek Nazarevich and Matheson, which shows that as you really get to some of the very heavy nuclei, fission goes by cluster decay. We don't have any evidence for that, but it seems that that could be a very important signature to look for. So the fission aspects, while the neutron-star merger with the electromagnetic signatures did not see directly this rare earth peak or the actinides, perhaps the evidence is already there. And if it's there as a result of fissioning to lighter nuclei, if we could specifically determine what those lighter nuclei were, that would be in the data. So that's an uncertainty that could be solved. There's a lot of calculations out there. This is one by Nicole Vosch and collaborators, basically saying that the fission peak can be like this, with 3 peaks, with fragments that are in the lighter 110, 120 mass range. If that's true, then we should be able to specifically pick out from the electromagnetic transients what they are and actually measure them. The more sort of daring idea is to look at nuclear weapons test debris. You might wonder, where did this come from in the middle of a science talk? But the art process idea was actually born from nuclear weapons tests. It wasn't until people used uranium in a nuclear weapons test and found that they had californium that the concept that there could be this rapid proton capture process came into place. And while weapons tests were ongoing, there was a big effort to try and see if the super heavies were made in weapons tests. I show here 3 tests. I've picked these 3 because they were reported. And in fact, the 3 tests, so the blue is the Hutch device and the red is the mic. The mic, so-called mic, is a 10,000 kiloton test. And you can see that it didn't make as many neutron-rich products as one would have expected. But the Hutch, which was a 20 to 200 kiloton device, did make quite a bit, and these are in the number of atoms. So imagine that in the 70s, people were measuring like 10 to the 18, 10 to the 20 atoms that were being produced of these very neutron-rich nuclei. In this region, I indicate where einsteinium and fermium are, and these were remarkable productions for those tests for making these very neutron-rich nuclei. The problem is they weren't thinking about the fission fragments at the time. They were just trying to push heavier and heavier in the actinides. So they might have missed the opportunity. But those debris from all these tests still exist. And actually, the longer-lived components can now be measured and be verified with the signals from the electromagnetic transients that were measured. So the question of could the R process, this rapid neutron capture process, make the super heavies? It's possible if through cluster decay that has been shown that it's quite a viable effect. And I noticed on the IN2P3 website that you have just a new measurement of bismuth with cluster decay. So it's quite possible that all of this is happening, and we might have the signatures at our fingertips to be able to test all of the simulations that are being done. So I wanted to end there with saying that we've learned a lot in the last 50 years, but a lot is still to be understood, and we haven't learned it all, obviously. And nuclear astrophysics just benefits directly from all the nuclear physics and high energy physics experiments with baryonic interactions, revisiting fission, looking at nuclear structure, nuclear reactions, weak interactions, and even using the neutrino signatures with gravitational signatures. There's much to be learned and to be answering all those open questions that still persist today. So thank you very much, and I'd like to congratulate you again for your 50th anniversary.
Thank you, Annie, for this beautiful travel. Are there some questions to Annie? We have time for one or two questions. Yes.
Thanks. Thanks, Annie, for this nice talk. I have a question. You showed the frequency distributions for the binary neutron star collapse, and you were questioning about whether it would go up to the actinides, but you also showed a simulation that seemed to reproduce that. So what were the processes or the ingredients of the simulation, just to try and understand what's going on?
The simulation actually is a simulation for a two-neutron star merger situation, but what I'm referring to is no direct evidence that that simulation or that the actinide population is there. That's what I would like to see, sort of a more direct evidence that you are doing that.
Okay, so I think time is running. So there is, sorry, there is no more time for additional question. Thank you very much, Annie. It was a beautiful talk.
There, Roger?
Yes.
Okay, fantastic. So it's my very great pleasure to introduce this afternoon's next speaker. And Roger, maybe your camera is a bit low. Yes, there you are. Now we can see you. Still there, Roger? Yes, okay. So Roger is Professor Roger Blandford is a reference in the fields of astronomy, astrophysics, and particle astrophysics. He is quite well known for a process he described with Roman Znajek on the way you extract energy from a rotating black hole and then put that into a cosmic particle accelerator. It's not his only scientific achievement, but that is, I think, something he is quite well known for. He was also the director of the first director of the Kavli Institute at Stanford. And as it happens, his deputy director, Steve Kahn, is giving the next talk today. He's here with us. And he is currently the chair of the Astroparticle Physics International Forum. So it's quite amusing. If I did my research well, Roger, I found that your first publication was with your PhD supervisor, the Royal Astronomer, Sir Martin Rees, and it was entitled A New Model for Variable Radio Sources. And it was published in September 1971. So that's exactly 50 years ago. So it seems quite appropriate that Roger now completes this century of contributions to science, or 2 orders of magnitude in time, as he would put it, with this talk on particles from the universe the next 50 years. So the floor is yours, Roger.
Well, thank you very much indeed for that kind introduction. Can you hear me?
Yes.
Excellent. Okay, so I'm very pleased to be with you and honored to be asked to participate in your celebration of your 50th anniversary, and even more regretful that I cannot be with you in person. I've been looking forward so much to coming to this, but it turned out not to be possible for reasons we all understand. And but I hope very much to come and see all of you in Paris as soon as it is practical to do so. So I'm looking forward very much to doing that. I was asked to give this talk, and I sort of slightly perverted the name of your symposium to entitle my talk From Particles to the Universe, to Particles from the Universe. And I was going to try and say a little bit about looking to a crystal ball for the future. What I'm going to say, I think I've been influenced by many people over the years, including Roman Znajek, I should say, who's not actually on this list, but with whom I'm still very much in contact. Here are some of them, all of whom should be credited for good ideas and not blamed for bad ones. So if I just start, and I'm not going to rehearse any of this, but I think we've had 100 years of discovery in what you might call cosmic particle physics. The history is well known, I'm sure, to most people in this room, going back to Hess in 1911, the discovery of cosmic rays, which of course was the birth of particle physics, with positrons, muons, pions, kaons, and so on, all being identified from the sky before accelerators took on the job. And I'll return to that point at the end of this talk. There was also, of course, in terms of the electromagnetic spectrum, the birth of X-ray and gamma-ray astronomy, and I'll say more about gamma-ray astronomy here, but X-ray astronomy is really wrapped up with it. And in 1962, there was the first X-ray source and the X-ray background and so on. And then also the third particle, if you like, that I'm going to just talk about here are the neutrinos. And to complement Professor Kajita, I will push up to the, if you like, the energy frontier and talk about the TeV and possibly PeV neutrinos, complement the beautiful work that's been done at lower energies. So it's going to be sort of theme here is to push up and the up the spectrum. So in some sense, this is the energy frontier, if you like, and I'll talk about the extremes of cosmic rays, gamma rays, and neutrinos, and as I said, speculate a little bit about the future, and I hope complement the scene setting that Professor Murayama gave us at the start. So let's just start now with the cosmic rays. And as you all know, these are observed actually from below GeV energies, but from mildly relativistic GeV energies, certainly up to ZeV energies, probably in their sources. And the spectrum is very crudely described by sort of three sections, if you like, from GeV to PV energies, which I say relatively little about, which is now mostly associated with supernova remnants. And I will say a little bit about the sort of upper end of this, which are the PV particles, 10 to the 15 electron volts, and the sort of phrase peritron has been attached to them, and I'll say a little bit more about that. Then there's a sort of spectrum, sort of known anatomically, I suppose, as that's something that's called the knee in the spectrum, and you can see the spectrum over here on the top right-hand side. And then there's a region up to roughly EV energies, which is sometimes called the ankle in the spectrum. And then you might call the foot in the spectrum, going up to the ultra-high energy cosmic rays up to, as I say, ZeV energies, not confidently detected as yet, but possibly existing, quite possibly existing in the sources. This, of course, has become anatomically much more complicated. There are several knees and several ankles and so on. I won't go through all of those details in any way. But I would point out here that the energy of the very highest energy cosmic rays that are seen are hundreds, up to about 100 joules or so, and that's a well-hit soccer ball, for example. It's also, for those who are worried about it, it's the momentum of a snail, and if you're going to be hit by one, that's the momentum that matters. And just for comparison, of course, in terms of actual energy, rather than center mass energy, the LHC is down at the 10 tera-electron volt range. One of the things we know about these cosmic rays, and known for a long time, is that they have to be accelerated up to these energies. We have good astrophysical reasons, like the gamma ray background and so on, not to believe that they are not top-down sort of exotic processes at much higher energies and just sort of showering down, as it were. They are pushed up to that energy from below. If we look at the ultra-high energy cosmic rays, I say I'm going to emphasize the intensity front, the energy front, excuse me, here. Then oversimplifying a much more complicated discussion, it's at least consistent that we're looking up to what we might call a rigidity limit, and it's more important to think in terms of the models of these sources, in terms of rigidity, the momentum per unit charge, and somewhere around about 8 exavolts over C in terms of momentum per unit charge, but with the energies coming from the increase in Z as you go to the highest energies. Now, there's still some bit of controversy about that, and I don't want to get into that, but this at least is an interpretation of the spectrum that's seen here in this second graphic. You don't expect too high an energy, much more than the energies I'm talking about, because photopion production, photodisintegration, and so on will limit the range of those particles on the microwave background. And there are, of course, other ways of detecting these particles, but mostly they're seen by direct detection in the atmosphere. Another big development, particularly from Auger, has been the measurement of a convincing anisotropy, dipole anisotropy. There are also claims of much smaller anisotropies, and those are not as significant as the pure dipole anisotropy. But I think it's a reasonable expectation that we're looking at the dawn of cosmic ray astronomy, and we could well see before too long significant identification of sources in the cosmic ray sky. We'll have to wait and see, of course, what happens. So if we think a little bit about the sources of the ultra high energy cosmic rays, then there are many possibilities out there. Some of them I think we can confidently rule out, but historically they've been there. If we look at, as I mentioned, as I said, the ones below a peta-electron volt, they are mainly associated with good phenomenological evidence with supernova remnants. And we look in the intermediate Shin-type cosmic rays between, say, a peta-electron volt and an extra-electron volt. That's about 1,000 in energy. The favorite sources that have been discussed and explored and in some cases advocated are neutron stars, and I'll say a little bit more about those coming up. And those are neutron stars associated, like the Crab Nebula, but also the more strongly magnetized one, which I'll say a little bit more about in a moment. And then there'll be associations of supernova remnants. It used to be a word long ago. There are other words that are used nowadays, but my French colleagues used to call these snobs for supernova OB associations. And they're basically lots of hot stars in a small cluster. And the thought was that they are able, and they're still thought about, as being able to accelerate particles in the Shin region up to around between a peta-electron volt, say, and an extra-electron volt. If we go up to the very highest energies, then your options are limited. And one of the reasons is that a very simple argument that can be given is that you want to take a particle and accelerate it up to, say, a zeta electron volt, it has to go through a zeta volt of potential difference one way or another. And if you associate that with a sort of EMF or voltage, then in the sort of optimal electromagnetic type of model, then you're going to be looking at power that's sort of V squared over the impedance of free space, twiddles 100 ohms. And that means that you're automatically, for protons, looking at luminosities of a quasar or a gamma ray burst or something like that. And if you're prepared to take the evidence that as you go into the highest energies, you're looking at nuclei with higher Z, all the way up to iron perhaps, then you can reduce this. But you're looking at very energetic sources and active galactic nuclei and gamma ray bursts and highly magnetized young neutron stars and so on. There are not too many other options outside the sort of very exotic and innovative, which could still yet be the explanation. Whoops, so go back again. So if the ones that have been mostly discussed, and I think that if you took a poll amongst cosmic people who work in this business, probably the favorite would probably be an active galactic nucleus of one form or another. The problem with using a quasar, of course, is there's lots of photons around, and those cosmic rays are subject to sins of transmission as well as emission, and so they have to get out in a dense photon background, which is not easy. A sort of generalization of these snobs or OB associations is the same thing happening in the nucleus of a galaxy. As starburst galaxies have been widely discussed. And a third possibility that's been discussed since the early 80s and so on, and I'm actually take even more serious than I did then, is an idea of a galactic wind termination shock being essentially being a stepping stone from galaxies like our own all the way up to even larger intergalactic shock waves. And so one thing that my colleagues and I are thinking about at the moment, and I will advertise a little bit here, is a hierarchical model that essentially relies on galaxies like our own to get you up to PeV energies. Then the winds associated with these galaxies and the shocks associated with them accelerate particles up to roughly EV energies. And then beyond that, this is in very round numbers, then beyond that, they are input or seed particles for larger intergalactic shocks associated with clusters of galaxies here, and the closest one being the Virgo cluster, which could conceivably at some point become a source. And here one sees further acceleration up to the very highest ultra-high energy cosmic rays, and they get as fast as they can from this acceleration site to Earth for the gratification of cosmic ray physicists. To say a little bit about this generic diffusive shock acceleration process, then it's the same process but scaled differently in these three sites, and that has a unshocked gas coming in, passing through a strong shock front. The downstream gas is approaching the upstream gas. Magnetic inhomogeneities allow particles to rattle backwards and forwards across the shock front, systematically gaining energy. In the context of a supernova shock front, the GeV particles are confined very close to the shock front, the TeV stray further upstream. And the idea is that the PeV particles, the very highest energy particles, get so far upstream that they can actually escape. And these shock fronts should be seen not just in terms of the transmission of the bulk of the cosmic rays, but as sources of the very highest energies, which are the ones that escape upstream, are in this picture responsible for the turbulence that creates the scattering, which creates their own acceleration. So turning to my second particle, the extreme gamma rays, here there's been a lot of excitement recently from again looking at the frontier, going up to PeV energies. But we should not forget that the huge success of the lower energy space-based like Fermi and ground-based detectors that have opened up gamma ray astronomy, showing us many, many sources in the GeV and TeV range, in fact, going back to 100 MeV and so on in the case of Fermi. And this has completely opened up the sky, and we now know of many different types of sources and understand their properties and how they emit and so on. I'm not going to discuss those here. I'm really going to keep obsessing about the energy frontier and pushing up beyond this range. And here some of the excitement has come from the observatories like Hawk, and then in Mexico, and LASSO in China, and Tibet also, well, in Tibet, of course, and they have been, it's a very exciting time in this business because there are results coming in. They're obviously a little bit tentative. It's very much a work in rapid discovery phase. And so here's just a sort of cartoon that Fang made, and I've sort of amended, and just some of these sources that have been seen. There's the Crab Nebula, we know it's a prodigiously effective particle accelerator. They're now seeing aboard a peta-electron volt gamma rays from it. It looks like they're created leptonically from electrons through a combination of synchrotron radiation at lower gamma ray energies and Compton radiation at highest energies. By contrast, we're seeing sources associated with supernova remnants and associations of supernova remnants like the Cygnus cocoon and this source G106. And again, seeing 100 TeV gamma rays, which means that the particles are being accelerated to even higher energies, about PeV energies. And in the context of the diffusive shock acceleration, which I've just outlined, I would say the message, if this holds up, and it's looking pretty good, the message is that nature is smarter than we are, because we really have to struggle to explain how these sources can accelerate to such high energies and to be at least candidate pevitrons. And so, so that's a very exciting challenge into the interpretation. Binary X-ray sources, the X-ray binary, SS4 through 3 has got jets, and it too has seeing very high TeV gamma rays, probably associated with the jets creating beams shown here, probably leptonic emission. And then in our galactic center, Tibet has seen a concentration of sources towards our center. We don't see too far away at the very highest energies because the range of those gamma rays is short. But as was conjectured some time ago, our galactic center may well itself be a pevotron, and we may see PeV cosmic ray protons being routinely accelerated either by the supernova remnants themselves, or conceivably in the scheme I just outlined, coming back to the galaxy upstream from a galactic wind termination shock. So this is a very exciting time in this business, and as I say, we're learning a lot. And if I'm giving this talk in a year's time, I'd have to rewrite all these slides, because these are detectors that are in development, and we are learning and as they accumulate more observations, we'll learn a lot more. So if I go to the sort of sources, I'll just say a few words here about the sources. Over here, you can see the famous Crab Nebula, a picture in the optical and the X-rays, and you can see jets. Once again, the idea jets are very common in astrophysics. In this case, they're formed by a spinning magnetized neutron star, and sort of simple principles of electromagnetic induction give you energies of 50 petavolts. And so they're obviously candidate pevotrons, and so it's not unreasonable that the Crab Nebula be a PeV gamma ray source. If you want to go to higher energies, then you'll go to bigger batteries associated with active galactic nuclei, and back there. And spinning black holes can do much the same thing as a spinning neutron star. So I'm sure this is okay back there. And so here we've got down here a spinning black hole, which when threaded by a magnetic field can create these enormous potential differences, which, as well as making the jets, can in principle give you the very high energy gamma rays and cosmic rays, the very high energy cosmic rays. Then, EMFs from a modest spinning black hole like that believed to exist in the M87 galaxy, in the nucleus of that, where there's this famous Event Horizon Telescope shadow of the black hole seen here. This, of course, made jets on scales that go all the way out, and in some other sources, 1 billion times the size of the black hole. So there's this tiny solar system size spinning source in the middle that is able to illuminate, in the case of M87, keep the surrounding gas in the cluster of galaxies hot and stop it from all crashing into the galaxy. Sorry. So we've got a lot of, so that would be a good, as I said, a good candidate source for the highest energy gamma rays as well as the cosmic rays. The gamma ray bursts can in principle create EMFs as large as 30 zettavolts, that's 3 times 10 to the 22 volts. And but there again, they're extremely luminous object. There's a very high photon density, of course, and the problem, as with even more so than with the AGN, is getting the gamma rays out of them. There's also a problem of whether or not there are enough of them close enough to us that we can actually see the highest energy cosmic rays, but it remains a sort of interesting type of source. And then, of course, there's for the lower energies, we know that the galactic cosmic rays are themselves the sources of these gamma rays, as I just mentioned, as the empirical evidence for them. So if we now look on to the neutrinos, again, a lot of interest and a lot of activity after a lot of hard work opening up, in some sense, neutrino astrophysics. We now, particularly from IceCube, been able to see sources of neutrinos up to about 4 petaelectron volts. As you go to higher energies, you can see here, the fraction of the neutrinos that you are looking at that are not atmospheric, and therefore presumably astrophysical, gets higher and higher. And this is obviously a more detailed argument, but it does look like we're seeing astrophysical neutrinos from IceCube. And of course, there's been a lot of activity looking with multi-wavelength and multi-messenger astrophysics associated with these detections of these astrophysical neutrinos. And I would like to make a small commercial here that with all the investment in these large facilities, relatively modest investment in radio and optical observatories pays you great dividends in this multi-wavelength, multi-messenger era. And so don't forget them too. The other sort of frontier here, of course, where there aren't as yet the detections, but there are almost certainly assured sources, is the so-called cosmogenic neutrinos, or ones that are associated with the GZK background, so the limits to the highest energy cosmic rays, where they create photopions and so on, which limit their range. Those will also, of course, create neutrinos, which are in principle detectable, and there are Gen 2, which is a sort of evolution of IceCube proposed, KM3net, which is very much under the in process, and by what the Russian experiment in Lake Baikal and other ones too, actually, are all hoping to push the energy frontier in neutrino astronomy up to higher energies. So if we say a few words here about the sources, as I said, there have been these attempts to find associated sources, and a prominent type of source that's being discussed are the jets, as I mentioned, associated with AGN. Sometimes these are called blazars. There's one particular one that IceCube claimed a possible identification with. I don't think it's thought to be, it's not thought to be a secure or a 5 sigma, if you like, detection. It's this TXS source, but it remains that these jets are really good candidates for making these neutrino sources. It is said that they cannot be the majority of the astrophysical neutrino sources, but I'm not personally not sure that that's a totally correct argument. It could still be the case, but there are no shortage of other candidates. The gamma ray bursts have been invoked in the context. And just say a few words here about gamma ray bursts, because they're part and parcel of this story, and you just heard about them in the last talk. There are now three types of gamma ray burst: the massive star supernovae, and those make jets. There's the binary neutron star mergers you just heard about. They also make jets, and so they become obviously good candidates for making these very high energy cosmic particles. And then there's the magnetars, which I'll say a little bit about, because this is, again, a very exciting frontier in astrophysics. These are what were originally conjectured and are now pretty firmly believed to be responsible for a third type of gamma ray burst. These are neutron stars that don't have magnetic fields as small as 10 to the 12th Gauss, but instead have 10 to the 15 Gauss, 30 times the Schwinger field. And there's a very exciting developing field pushing QED into this non-perturbative many-body regime, and the possibility of doing important and interesting and relevant experiments at light sources and so on. The other thing that's happening, well, two other things that are happening here over the last year, an astronaut physical phenomenon called fast radio bursts. There's now a lot of circumstantial evidence that at least a lot of these are associated with magnetars, these highly magnetized neutron stars. And to find out more, NASA has launched a small explorer satellite 3 days ago, I think 2 days ago. This is called IXPE. It's been launched successfully. Let's hope it works successfully. And it will do X-ray polarimetry, which will be very diagnostic of magnetars and other sources. Another type of source that's been associated with neutrinos are the so-called tidal disruption events, which we now have a lot of very good examples. And these are when a star strays too close to a black hole, particularly in the galactic nucleus, then it gets ripped apart tidally. And that also produces lots of electromagnetic emission, but could also be a credible source of neutrinos. And people have been looking with the Zwicky transient factory and looking for spatial associations, nothing 5 sigma-ish yet, but certainly it's a work in progress. And as Steve Kahn will tell you about the Vera Rubin Observatory. This is set up to do many things as well as dark energy and the transient astronomy it will do. will really, one hopes it will really settle this matter, whether there are associations with neutrino events or good upper limits from this. So it's a very exciting time, as I'm hoping to communicate in this business. So what I'd like to do now is just say a few words sort of in parting about where the field might be going. I hope I've been able to communicate there's a lot going on, and there's discovery on the timescale of months to years rather than decades happening in this business, and it's relevant, I think, to particle physics. Now, I think there are three ways to think about the future in the general business of astroparticle physics, and I'll take the first one. First one is what I would say used to be called the reluctant conservative, and this here the posture is that in terms of particle physics, we've got this brilliant standard model. It's been spectacularly validated. It continues to do this. All the tensions and so on go away. There's no significant departures from the standard model insofar as it is relevant. I think there's dark matter. There's no escape. If you believe it's a particle, then there's really no escape from a WIMP sector probably at this point. This will be explored using accelerators and searches. There will be exquisite limits set and so on. But people won't really have any positive to get on with. They'll just know what it isn't, as we've done in that session. And the neutrino sector will essentially be completed by experiments in progress or in preparation. I think CMB has a good chance of getting a lot of the answers in perhaps first, but we'll see. That'll be an interesting thing how that works out. The masses, of course, the hierarchy, whether or not there's any measurement of CP violation, but that will be about as far as it goes. Cosmology, again, like particle physics, is a brilliant standard model. It's spectacularly validated. No significant departures as far as it goes. Lambda is just a cosmological constant, which is most sensible, always been the most sensible thing. And it's seen increasingly as the physics of the large, not as an expression of quantum field theory, in much the same way as oceanography and meteorology don't really care about molecules. So it's essentially seen in that way. The dark matter is dumb and useless in the sense that it's not a probe of anything, it's just a source of gravitation. And, and for those who want to push further, there's the sort of slightly depressing prospect that galaxies will behave much more like people than particles, and their idiosyncrasies sort of outdo large N in terms of using them as tools for exploring the behavior of fundamental physics on the cosmological scale. And then for the cosmic particles, we continue to be limited by the flux of them. We're not really able to get fed too far around the intensity frontier. So that's a slightly depressing, reluctant conservative view. Against that, there's a sort of exuberant optimist view, which is that the quantum gravity and string theory and so on will be solved by pure thought. They'll be integrated into particle physics and cosmology. There will be measured deviation from, in the concept of cosmology, measured deviation from flat lambda CDM. And these will be accounted for in this fashion. There'll be a detailed deductive theory of inflation, a clear view of the multiverse. Some of the expressions of this type of physics will be seen around astrophysical black holes. Propagation effects may be detected and so on. That's a very optimistic view. And in particular, I think that what seems to me the really big problem with this whole area is what is dark matter. This turns out to be a sector that's rich in new physics, just like the muons and the pions and the kaons, new physics principles. And then furthermore, there's a deductive theory of dark matter and baryogenesis that explains, as we just heard in the last talk, why we're here and so on. So that's the sort of exuberant optimistic view. And before I go on to the third view, which I would like to say something about scientific discovery. And this is from the perspective more of an astronomer than a physicist. But if you look through these lists of these big discoveries, a little bit tongue-in-cheek in some cases, the history is always a bit more complicated. But the CMB, the quasars, the stellar black holes, the massive immutable neutrinos, all of these things, if you just read down this list, I won't read it all out for you, pretty well everything was discovered, or the discovery was initiated by people trying to do something different. And it was sort of accidental. Now, one way you can interpret this is to say that astronomers really don't know what they're doing, And in some sense, that's right. But I will say in defense of my colleagues, they're awfully good at following up hints and making discoveries. But if you look at it, even at the history of particle physics, most of it has been unscripted. And I think, you know, too often people are sort of planning big experiments to measure numbers in a well-defined scheme, rather than allowing the discoveries to happen at the interfaces. In some sense, this is the perspective of the observatory over the perspective of an experiment. And one should really allow in one's planning and one's big facilities as much possibility for discoveries, because the discoveries can be highly relevant to what you set up. So that was the point I was going to make in sort of preface. And then I think my, you know, final slide here is that, and I would, for me, it is a reasonable expectation, there will be steady progress in experiment and theory, in particle physics, and in cosmology. I'm particularly taken by the prospect that we learn more about the cold equation of state, as we heard in the last talk, for nuclear, which is very important for relating to the masses which we're measuring of neutron stars, and also this new territory, I think, which is the QED beyond the Schwinger field. And I'm sort of optimistic that there will be steady progress in that. And in the sort of observational sort of astronomy frontier, if you like, there's going to be there will be progress in cosmic rays, in gamma rays, in neutrinos. And I'm sort of optimistic in a way that I think particle physicists are not, that the cosmic particle physics will actually constrain particle physics. I think there's a sort of disdain for cosmic ray physics sometimes amongst accelerator physicists, which you might interpret as a form of matricide, but it's also, I'm sort of a bit more optimistic that, you know, going to 100 times the accelerator center of mass energies, improved shower models and so on, will constrain physics that is at energy scales that are inaccessible to accelerators. One so simple example is the, people got worried, as you all know, about LHC's ending life as the LHC ending life as we know it by making black holes. Cosmic ray physicists were able to say, well, nature's performing this experiment on a regular basis, and we seem to be okay so far. So that's a sort of almost trivial example, but I think more subtle things are possible. There will be a push to higher fluxes, going through the intensity frontier, if you like, higher energies. Anisotropy will get better, the spectrum will get better, and consequently the composition. And new sources will be identified. We've got all this transient astronomy coming online, and these sources are not going to be able to hide much more. On the instrumental front, there's GEM-USO and POEMA. They are sort of trying to increase the number of events by looking from satellites from space around the Earth. And something I thought about just while preparing this talk, and I really have not thought much about it. I'm sure others have done, and it may be silly. But is it possible to think about an orbiter around the moon with very fast electronics, looking for impacts of very high and ultra high, especially ultra high energy cosmic rays, hitting the lunar surface? Could you possibly see enough of a flash from the hard surface of the moon rather than from a shower in an atmosphere? So that's just a thought, and I expect people will be able to tell me that this is silly, but I wasn't able to demonstrate to myself that it was silly. But I think that my biggest point is that came from the last slide is that we can look forward to new sources, new physics. From the point of view of astrophysics, I don't know what these sources are going to be, but I'm going to call them, in the spirit of the field, quasars, grazars, and nusars for these three particles. And I think, there's still lots of discovery out there to be had. I think it can contribute to physics. And the final thought is, and this goes back to the history of this business, synchrotrons and plasma accelerators and so on. A lot of that came from people thinking about the cosmos and the laboratory together. And John Dawson and others did that. And so I would say even those who are trying to make the big particle colliders of the future could well muse about cosmic cosmic accelerators as we're learning about them and as we're defining them for inspiration, because that's certainly happened in the history of this field. Thank you very much indeed. I'm so sorry I can't be with you. I wish you the happiest of birthdays, and I hope that there'll be even more in the next over the next 50 years than I just speculated about in the last couple of slides. Enjoy your party.
Thanks, Roger. Maybe I have time for one question if there's any question in the audience. If there's none, maybe Roger, you haven't said much about the frontiers in theory. Where do you see currently the theoretical field in astroparticle physics going, and what are the challenges?
Oh, I think there are many. Well, two things. One is the accelerators we know about we're learning about them from a theoretical point of view, from some extent, just thinking more about what's going on, but a lot of it's coming from simulation. And I think that is helping a lot. So the diffusive shock acceleration, various types of direct acceleration, other types of second order processes and so on. We're learning about the physics of them a lot from simulations, but I would also say that we are being confronted all the time with new challenges from the rapid, as I've tried to emphasize, the rapidly developing observational position, the fact that pevitrons do look like they exist in the galaxy, and we're sort of rushing to catch up in some sense as theorists, trying to explain how nature is cleverer than we are. So I think the new challenges and these simulations especially influencing our view of what happens in the sources as the observations improve.
All right, so moving to the next presentations, you can please. So 20 years ago, roughly, a new term enters the physics vocabulary. It's dark energy, which was used to explain the acceleration of the expansion of the universe. Now, giving it a name was a first step. We now want to know what it is, and Steve will tell us everything about dark energy. Steve.
Great. So let me thank you very much for inviting me to this 50-year celebration. Just from my personal perspective as the director of the Vera Rubin Observatory, which most of you probably know as LSST, its former name, the role of IN2P3 in particular in the French community has been extremely dramatic. Roger and I first came to Paris, I think in about 2005. It was shortly after CIPAC, the Kavli Institute at Stanford, was formed, and we formed a sister institution relationship with APC here in Paris and came for a very nice signing ceremony over in the 16th arrondissement. I came back about a year later to talk about French involvement in this project, which was the largest investment by the National Science Foundation, Department of Energy, in a future cosmic physics facility. And I was just overwhelmed at the interest. Many of you may know that there are a large number of IN2P3 laboratories involved in this project. And I've had the pleasure over the years to make trips to Paris, to Marseille, to Lyon, to Clermont, to Grenoble, and all the various places where people from this fantastic institution have been involved. Another point to make is while we talk about fundamental cosmology and dark energy, I think the French particle physics community sort of led the world in recognizing the cosmic frontier as a key part of its research. And, on the US side, NASA, NSF, and DOE were a little bit later to come to that realization.
It's now clear that cosmic investigations are absolutely key to fundamental physics, but I think that realization occurred much earlier in this particular time zone. So congratulations to all of you on the 50 years. So my task is to talk about dark energy, and I know we're late on time, so I'll try to speed through some of this introductory material. I think everybody's aware that this discovery came in the late 1990s, and it was widely hailed as perhaps the most significant development in fundamental physics in over 50 years. And of course, about 12 years later, they awarded the Nobel Prize to Saul Perlmutter, Brian Schmidt, and Adam Rees in 2011, and many members of the French community were involved, at least on the Perlmutter team, and I think possibly also on the Schmidt and Rees team. Why was there so much interest in this? And it's because dark energy is one of those topics that just touches a lot of the things that we hold most dear. Many of you know Michael Turner, a famous cosmologist in the States, who said, we know less than zero about dark energy. It's not just that we don't know what it is. It kind of screws up the things that we thought we did know, or we thought we did understand. And that mystery is so profound that it cuts to the core of our understanding of physics in general, and of course the nature of the universe. So, you know, what is it for those of you who may be less familiar? Dark energy refers to the fact that the universe is not only expanding, its rate of expansion is increasing with time, it's accelerating. And that, of course, is quite counterintuitive. We think of gravity as an attractive force, so we think that the expansion of the universe should have been slowing down with time. The existence of the acceleration requires something else, some mysterious medium that permeates all space. That medium carries energy, but does not, at least to this stage, we don't know that it interacts with any other of the constituents of the universe, including dark matter, which we also don't know what that is. So that's where the term dark energy came from. This topic has an interesting connection to the notion of gravitational instability. In fact, not everybody's aware of this, but Isaac Newton recognized early after developing his theory of gravity that if the universe were infinite in extent and in time, then it would be gravitationally unstable. And this is a direct quote, well, from the Latin. It seems to me that if the matter of our sun and planets and all of the matter of the universe were evenly scattered throughout the heavens, and every particle had an innate gravity towards all the rest, and if the matter were evenly disposed throughout an infinite space, it could never convene into one mass, but some of it would convene into one mass and some into another, so as to make an infinite number of great masses. So Newton liked that idea initially because he thought maybe it explained the origin of stars. However, he soon realized later that the stars, given infinite amount of time, would then fall into one another. So one couldn't maintain a static universe with that theory of gravity. And at that point, he just said, well, this proves the existence of God, because God must be there to keep the universe from collapsing. Some might say that our current models of cosmology invoking at least 3 deus ex machina are not that much better than Newton's conjecture, but we'll see. Of course, gravitational instability was also the motivation of Einstein. When Einstein reformulated Newton's theory of gravity into general relativity, the model involved the existence of mass and energy curved spacetime and its surroundings. And of course, the apparent gravitational forces are the result of motion through this curved spacetime. A uniform universe would also be gravitationally unstable, of course, in this new theory. And since Einstein preferred the idea of a static, infinite universe, that wasn't going to work with his equations, so he threw in an additional term, which was actually an integration constant. So it wasn't mathematically invalid. It was entirely reasonable to say there's an integration constant. He called it lambda, and he adjusts the value of lambda to keep the universe gravitationally stable if it were static. Of course, not long afterward, Hubble and others discovered that the universe is not static, it's actually expanding. And so Einstein quickly abandoned his cosmological constant, and as is well reported, he called it his greatest blunder. Now, of course, we know that there is a cosmological constant. It's just got a funny value to it. The concept of cosmological constant actually arises quite naturally in quantum field theory due to zero-point quantum fluctuations of all the fields in the universe, which impart energy density to the vacuum. This results in a medium that carries positive energy density but negative pressure. So in general relativity, not only energy density but also pressure contribute to the curvature of space-time and acceleration via this equation, which I've written here. And you can see that if P is negative, then it's possible to actually get a universe which is positively accelerating. So the way this is usually referenced is in terms of what's called an equation of state parameter W, just the ratio of the pressure to the energy density. And as you can see, if that is less than minus 1/3, then you would get a positive value of A double dot. A pure cosmological constant occurs if W is equal to -1, which is independent of density or of A or of Z, and then it's impossible to distinguish between this integration constant and an actual field. They both have the same effect. So it's not hard to make a cosmological constant according to the physics we think we understand. The problem is that naive calculations of what it would be are off by about 120 orders of magnitude. That's by extending the zero-point fluctuations all the way to the Planck scale. If you cut them off at the TV and there are other considerations, then the problem drops down to 60 orders of magnitude, which is still a problem. So the issue is not how to generate a cosmological constant, but rather how to keep it small and non-zero. Another way of phrasing this is that the effective mass scale of the value of dark energy, the energy density carried in dark energy is around milli-electron volts. So it's very surprising that there would be new fundamental physics in the milli-electron volt regime, which we thought, of course, that we understood quite well. Another interesting element of this, which Hitoshi Murayama referred to earlier, is the so-called why now problem. You know, there are other components to the energy density of the universe. Early on, the universe was dominated by radiation, material moving relativistically. That drops off like the scale factor of the universe to the -4th power. Then we went into a matter-dominated regime, which drops off like A to the -3, and a pure cosmological constant would keep the density constant. So if you plot the relative fraction of radiation, matter, and dark energy as a function of time, then you get this plot, which is shown here on the right. And the problem is that our current cosmological model tells us that we live right here, which is a very unusually favored position on the plot. It's not so unreasonable that we would be dominated by dark energy or dark matter. What is unreasonable is that the energy density of dark matter would be close to the energy density in dark energy. There's no particular reason in the theory why that should be true. And of course, that evolves with time, so it's only true now. And that has motivated a lot of ideas that try to relate dark energy and dark matter to other problems in cosmology to explain this issue. Okay, so how do we study dark energy? Well, the only real secure observational handle that we have on this is through the Hubble parameter, which is the ratio, the logarithmic derivative of the scale factor of the universe. So we need a way to measure the Hubble parameter as a function of redshift or as a function of A. And you can do that by, finding a lot of galaxies, measuring their absolute distances somehow, and then measuring their redshift, and therefore inferring h of z. So the standard techniques are to measure the apparent brightness of standard candles, or measure the angular size of standard rulers. Those are both kinematic measurements. They yield a direct measurement of h of z. But another powerful approach, which has attracted a lot of interest over the last decade or so, is through measuring the growth of structure as a function of redshift. As stars and galaxies and eventually clusters of galaxies grow by gravitational instability as the universe cools, they provide a kind of cosmic clock. That process of gravitational instability, which I talked about earlier, is a reasonably well understood process. And if we can time it, how individual structures develop with time, at what redshifts, then that gives us another measure of h of z, and therefore of the expansion history of the universe. But growth of structure is more than just a measure of h of z. It's also a dynamic measurement. Its value, how it works depends not only on the expansion history of the universe, but also on the theory of gravity. And so a comparison of h of z inferences from measurements of kinematic measurements versus those of dynamic measurements like growth of structure can potentially distinguish between models that are pure dark energy models versus those which involve modifications to general relativity on large scales. And that's one of the holy grails in this field, is to try to decouple those effects. So I'll just run through this quickly, the standard diagnostics. Of course, the discovery of the acceleration of the universe came from type 1a supernovae, which are calibratable standard candles. There's been a huge amount of work over the years with a lot of French involvement. We now have large samples of type 1a supernovae. The next set of experiments will increase them by a factor of about 100 or so. But the issue is not really just the statistics of how many supernovae you have. It's more a function of the precision of your measurements, both the calibration of the photometry itself and all the assumptions that go into making corrections as the redshift of an object increases. And as I mentioned, this, of course, is what led to the Nobel Prize to Perlmutter, Schmidt, and Rees. A standard ruler technique, or the leading sort of standard ruler technique, is associated with something called baryon acoustic oscillations. So the very early universe was very hot. So all of the atoms, of course, were fully ionized. And basically, the universe was a sea of protons, electrons, and photons. In this medium, disturbances or slight overdensities give rise to sound waves, which, since everything's relativistic, travel at the sound speed of c over the square root of 3. But at some point, the universe recombines. That's where the CMB radiation comes from, and essentially becomes electrically neutral. At that stage, the sound speed drops to 0. So these perturbations that have been formed stop in time. And we understand that scale extremely well because we do understand the dynamics of the early universe very well. And that scale turns out to be 150 parsecs. And you can see it in the CMB, which is the well-known peak in the temperature spectrum of the CMB, at 150 megaparsecs. That gives rise to this scale, and it's very well measured from the CMB itself. But it leaves an imprint in the galaxy distribution as well. So following recombination, the gravitational instability we've been talking about causes the birth of stars and galaxies. The acoustic oscillations form an imprint in this distribution, and that actually persists as the universe expands, although it gets weaker with time. And so you can measure that effect by measuring the distribution of galaxies, either in 3 dimensions or 2 dimensions, and looking for these subtle oscillations, which you can make out here. Another technique which has yielded results already, although its precision is improving dramatically as time goes on, is associated with gravitational lensing and cosmic shear. Of course, in general relativity, the curvature of space-time not only affects matter, it affects light rays, so it gives rise to gravitational lensing, which is the deflection of light due to mass concentrations. We use the term cosmic shear to refer to the systematic and correlated distortion of the appearance of these background galaxies due to weak gravitational lensing by clustering of matter in the intervening medium. And so a given galaxy image is both displaced slightly on the sky and distorted due to that gravitational lensing. Now, for any individual galaxy, you didn't know what its shape was to begin with, so you can't infer anything about it. But if you measure a very large number of galaxies, then you can look for subtle correlations in the shearing of nearby galaxies, and that gives you a direct measure of the distribution of dark matter concentrations in the intervening universe. And so the simplest measure of this is a so-called two-point correlation function measured with respect to angular scale, plotted in the same way we plot the CMB. And you can do this in various different redshift bins, and you get the curves which are shown here, and you can see for different redshift ranges. And you'll notice these curves exhibit subtle points of inflection. That's a transition from the linear regime to the nonlinear regime. In the linear regime, the predictions of the theory are extremely good. There are not really any assumptions there, but the sensitivity isn't as high. As you go to high L, which is small angular scales, then the dynamics, the gravitational dynamics, gets to be nonlinear, so the predictions are more dependent on simulations, but the sensitivity is very high. In any case, this effect is extremely subtle. Because galaxies have individual shapes, we have to average over all of that by looking at huge numbers of galaxies in order to get down to the cosmological measurement. And that's required very large-scale surveys of the sky, which we didn't have earlier. Now, I mentioned using those imaging surveys, you need to put them in redshift bins, which means you need to know the redshifts of the galaxies you're looking at. Of course, galaxies have distinct spectra with characteristic features at known rest wavelengths. Unfortunately, for these very large number of galaxies that we use in these investigations, they're also quite faint, and it would take an enormous amount of telescope time to get redshifts spectroscopically of all of them. So the way we have to do this is by measuring the colors in a finite number of bands and trying to infer the redshifts from that. And this requires accurate calibration of both photometry and the intrinsic galaxy spectra as a function of redshift. And there are unfortunately a number of systematics associated with this, and this is one of the leading frontiers of the field. The accuracy is limited by statistical quality of data and the location of key spectral features with respect to the passbands which are used. The dominant features are the Balmer and Lyman breaks at 400 nanometers and 91 nanometers respectively. And as those move through the bands, you can see the noise on this plot, which is a plot of inferred photometric redshift versus true redshift. You can see that come and go, even with some catastrophic failures where you mistake the Balmer break for the Lyman break or vice versa. So this becomes a big issue. And the fundamental problem with it is at the very faint levels that we accumulate large numbers of galaxies, we actually don't know what the spectra of the galaxies are. This was an earlier time in the universe. The individual galaxy spectra are determined by the history of star formation as a function of time, and that makes it difficult to tell. And then another modern technique, which has been of interest lately, is something called redshift space distortions. So this involves looking at the correlation function of the galaxy density in three-dimensional space as a function of separation, both along the line of sight and transverse to the line of sight. And you might naively expect that that would yield a sort of circular uniform distribution, but it tends to yield a picture like this for a couple of specific reasons. If you look along the line of sight itself, you often see this long elongation, which is called the finger of God effect. And that's due to the fact that highly collapsed structures are in virial equilibrium, and there are peculiar velocities associated with the galaxies that are not just at their normal velocities following the cosmic expansion. Equivalently, on larger scales, you'll notice that the curve is flattened, and that's because at larger distances, galaxies tend to be falling inward toward concentrations. So on the top end, further away, they have a peculiar velocity in one direction and the other side in the other direction, and that tends to squash the distribution. The measurement of this effect is good because it gives us a measure of the fluctuations in mass density as a function of redshift, which is a curve of growth measurement that you can make with a spectroscopic survey. Okay, that's enough of an introduction. Let me just turn now to the two major new, what we call stage 4 facilities, which are on the horizon to advance this field. Both are US funded, and both have significant IN2P3 involvement. I mentioned Rubin earlier, but it's also true of the dark energy spectroscopic instrument. So DESI is a multi-object spectrometer that will obtain spectra of tens of millions of galaxies and quasars, yielding precision measurements of BAO and redshift space baryon acoustic oscillations and redshift space distortions. It was an instrument that's fielded on an existing telescope, the 4-meter Mayall telescope at Kitt Peak in Arizona, and they completed basically construction about just sort of at the beginning of the COVID period, and they've started operations within the last year. The second is the Rubin Observatory, which I'm affiliated with, which is a very large imaging survey. It's an integrated survey system that will do a 10-year-long survey of the entire southern hemisphere of sky. Every part of the southern hemisphere will be imaged 1,000 times, and that will yield a sample of something like 20 billion galaxies, which is far larger than exists today, and the statistical measurements of the galaxy distribution in colors, in redshift space, et cetera, is what will provide these subtle cosmological measurements. Rubin is a sort of 8-meter class telescope, so it's a very large facility, and it has a 3 billion pixel camera, which is actually the largest camera ever constructed for astronomy in the world, and that's where there's been significant IN2P3 involvement. And this facility is under construction on Cerro Pachón in Chile. We're nearly done putting it together. We need to commission it, and then we'll begin the survey in about 2 years. So just a few quick slides on each of these projects. This is a sort of overview slide of DESI. DESI aims to get spectra from basically low redshifts through the regime where dark energy took on and then beyond it to accurately measure H of Z in that critical regime. And to do that, they have to use different groups of galaxies. So at the lowest redshifts, they'll just look simply at the brightest galaxies. Intermediate redshifts, they'll use things which are called luminous red galaxies, which are reasonably well understood. At larger redshifts, emission line galaxies. And then at the furthest distances and the highest redshifts, they use quasars. The quasars will give a map of the matter distribution, but they also give information on what's called the Lyman alpha forest. You can see absorption lines along the line of sight, which give an independent measurement of the baryon acoustic oscillations. So DESI was put together in August 2019. It's a really beautiful focal plane involving something like 5,000 robotic positioners that involve fibers that are all fed into spectrographs, so you can simultaneously get a spectra of very large numbers of objects across the field. And this is a projection of what DESI will achieve. So this is H of Z as a function of Z. So obviously heading up toward the current era, this is the dark energy dominated regime where the Hubble parameter is increasing as the universe expands. And then there's this minimum here. And then as you go back to the distant past, you enter the deceleration regime. And the main point of this slide is just to see the comparison between the red error bars and what the current state of the field is. So this is a very dramatic improvement over our knowledge of the cosmic expansion. In terms of the Rubin Observatory, this is a very complex billion-dollar facility, 8-meter telescope, 3 billion pixel camera. We produce an enormous amount of data, hundreds of petabytes, so a lot of the investment in the project was in the data processing, and in fact, half the annual data processing for this project will be done here in France, in Lyon. I won't go through this chart. This is sort of a high-level summary of the performance of the observatory. Just some quick pictures. The construction is at an advanced stage. You can see the facility in Chile, the telescope itself, and on the camera, all the different elements of the camera have been fabricated. This is a picture of the focal plane, which involves, I forget the numbers slipping my mind, a large number of 4K by 4K CCDs, all very precision aligned. Everything is functioning, everything is working. This picture here, called the filter chain exchange system, That is the piece that was designed, fabricated, and tuned here in France, delivered to SLAC about a year ago. You saw it on the entering film, and they just went through this heroic achievement this summer to get the performance required of that system within the allotted time. So that was a great achievement. During the pandemic, people bravely came to the US and completed that successfully. And these are the dark energy constraints that Ruben will provide. So that inner contour, the smallest one in the center, is where we'll go to. And the current data are sort of more like these larger ellipses here. So you can see the kind of statistical improvement we'll get. Of course, this plot is made just around the lambda CDM paradigm. If there's a difference from lambda CDM, hopefully with that sensitivity, we'll see it. So what is the current state of this field? As Roger mentioned and Hitoshi alluded to at the beginning, lambda CDM, the standard cosmological paradigm, which includes a cosmological constant with W equal -1 and only non-relativistic dark matter, has been amazingly successful at explaining a wide variety of observations since the discovery of the expansion in the first place, of the acceleration in the first place in 1998. Just there have been a large number of tests, and they've all remained consistent. Now, in recent years, there's been some tension, and it's specifically involved quantitative disagreement between measurements of certain cosmological parameters from late universe optical surveys and their counterparts inferred from the CMB at Z of 1,000 or 1,100 or so. So the two which have received the most attention are measurements of sigma 8, which is the amplitude of primordial fluctuations in the universe, and H0, the Hubble parameter at Z equals 0. Both of these discrepancies are of order a few sigma, and some different methods have yielded inconsistent results, so the jury's still out on this. But this remains tantalizing because it's a departure from lambda CDM that we're looking for in order to get some insight into what's going on in the first place. So these last few slides just show you what those discrepancies look like. These are a series of measurements of sigma 8 versus the matter energy density fraction in matter from various imaging surveys, and the blue ellipse there is the CMB data. And they're at tension at the 90% level. So this is not a detection, but the different surveys are giving consistent results, and so there's something there, maybe. And then the Hubble constant discrepancy, which has received a lot of attention. This slide shows the Planck constraint on H0. What you get from local measurements depends on what you use to construct the cosmic distance ladder. The historical thing was to use Cepheid variables where the absolute luminosity is connected to their period of oscillation. And as you can see, the Cepheid constraint was quite at odds with the Planck constraint. The claim was about 5 sigma. And so this led to a lot of excitement that something was going on. However, there have been more recent studies done with what are called tip of the red giant branch stars, which are also good calibrators. And they're discrepant not only with the Cepheids, but they're much closer to the Planck value. So whether or not there is really an inconsistency in the Hubble constant remains to be seen. Okay, my last slide then, just looking beyond Desi and Ruben, you know, where is this heading? And what does the future hold? And unfortunately, we all, around the world, we all go through these processes of trying to do various survey committees to decide, you know, what to spend billions of dollars or billions of euros on for the future. And the problem, of course, is you don't really know what you've measured from the things you've already been building. The basic answer to what is the future of dark energy research is it depends on what we measure. If we continue to find lambda CDM works at this precision level, that's going to be both disappointing and kind of amazing that the universe would actually be so simple. So I don't view that necessarily as a negative result, but it is a possibility, of course. We will improve the constraints by at least an order of magnitude. If those tensions that I showed you on sigma 8 and H0 are real, They will be measured at many, many sigma, so that won't be any question anymore. Of course, the CMB constraints will also improve with future facilities. If there are other departures from lambda CDM, you know, the hope is that'll provide new clues to the origin of the cosmic acceleration itself, because unfortunately, just saying there's a cosmological constant doesn't actually tell you what it is, and it's hard to go much further from there. There are many, many theoretical papers out there. There's no shortage of ideas, so this field is going to remain data-driven for a long time. These are subtle measurements, and systematic uncertainties are likely to continue to provide the ultimate limitation. I mentioned the photo-Z systematics, which are especially important. At the faint magnitudes of Rubin, we just simply don't know what the intrinsic spectra of galaxies are. And they're at 27th magnitude, which would be extremely difficult to measure, even with the European Extremely Large Telescope, which will be a 39-meter facility. So, you know, how do we address that? After building the ELT, is ESO going to allow us to spend a lot of time looking at random galaxies just to calibrate this problem or not? Probably not. And so this is going to be a difficult problem that will still be with us. But there are creative ideas on how to address this, and a good fraction of the world is working together on that. And finally, there are other complementary techniques which is just being started, like 21 centimeter surveys, which give you full spectroscopic and imaging surveys at the same time, all the way back to high redshifts. They will probably also be invaluable. We don't yet know. And there are a number of projects that are in development in this area. But I think the most important thing, as it's true in other areas of particle physics, is the complementarity of the various probes is especially important. So let me stop there, and I appreciate your attention, and congratulations on the 50 years.
Thank you very much, Steve. So we have time for one question or one comment. Yes, please.
Yes, thanks for asking that question. So, the discovery of gravitational waves and the requirements for electromagnetic follow-ups are quite interesting. Rubin has a 10 square degree field of view, so it's the largest, very deep imaging facility in the world, and it's very well suited. Now, the intent for the observing program for Rubin is to conduct this systematic imaging survey of the Southern Hemisphere, not particularly to run around chasing targets of opportunity. But the LIGO and Virgo event rate is not sufficiently high that it would actually interrupt very much. So the real question is not so much can we move Rubin around to go look for a counterpart when an event goes off. It's that if you take a Rubin exposure, even one of our typical 15-second exposures, there will be about 10,000 things in the image that changed. Most of those are ordinary stars or asteroids or things you can sort of rule out. But it will still leave a fairly significant number of things that could be the gravitational wave event or might not be. So the real issue here is going to be how do we do that effectively, and how do we determine what are the measurements to make that will unambiguously tell us what of all of these things that varied during that period of time could actually be the trigger. Once we identify what it is, then Rubin stops. All the follow-up can be done with much smaller facilities once you know where the source is. So Rubin's job there is purely to try to find it. And if another world facility comes online, say in Japan or in India, then the boxes come down to about 10 square degrees, which matches exactly the Rubin field of view. With the current Virgo LIGO configurations, it's about 30 square degrees or so, but still we can do that in a limited number of pointings, so it doesn't take very much time.
Thank you very much, Steve. And I think we should end the session now. Let's thank again all the speakers. Okay. Thank you very much again for your presence here. Again, it was not an easy decision for you to make to come here, I'm sure, but for those who came from far away, thank you again. So, Ursula.
Dear guests, dear colleagues, dear friends, thank you very much for joining us for the celebration of the 50th anniversary of IN2P3 this evening, despite the difficult circumstances. Don't worry, I will just say a few words. It will not take hours. But I would also like to invite those who want to join me in saying a few words to come here, as Reynald just indicated. So IN2P3 is the National Institute of Nuclear and Particle Physics and has been founded by an official decree in April 1971, with his first director being Jean Théillac. Since then, IN2P3 evolved as all the living systems that you see around here, yet it was a little shorter time scale. IN2P3, in some sense, is the younger sister of INFN, and I'm very happy to see INFN directors among us, who celebrated their anniversary this year as well. It was the 17th, actually. And in a similar way than INFN, IN2P3 coordinates the research through about 20 laboratories all over France, affiliated to CNRS, the French Center for Scientific Research, and the major universities here. The event today concludes actually a series of celebrations that took place in all the IN2P3 laboratories throughout the year. And I would naturally like to thank Reynald, the 8th director of IN2P3, to inviting us all today for this closure event. I hope you enjoyed the illumination of 600 million years of evolution in these ancient royal gardens of medical plants. Our gathering this evening takes place here in the Gallery of Evolution, and the building that you see here dates from 1889 and was opened just a couple of weeks after the Eiffel Tower. Looking at this beautiful interior today, you would hardly believe that after the Second World War, this place was abandoned. The glass ceiling was broken. They fixed it just roughly, and in 1966, the whole museum closed down, and everybody was thinking that it will be destroyed shortly after. But thanks to many people who joined together, there was a huge effort made, and in 1991 the works for restoring this building have started. So please enjoy this evening the exhibit that is here and that I found truly remarkable in the way that it is organized. It's really a lot of specimens from the Museum of Natural History that you can find here. Now, in this area where you are today, there are also many other historic buildings. The laboratory of Henri Becquerel was just close to the amphitheater where we have been today. Marie Curie gave lectures just over the street. Her laboratory is a little bit higher up. There was Irène and Frédéric Joliot-Curie had their laboratories at Collège de France, which is also close by. Le Prince Ringuet was just a couple of streets away in the École Polytechnique, Yves Rocard at École Normale, and all these have been historical figures that paved the way to come to IN2P3 in the 70s. So with the accelerators growing, a discussion started in the early 60s about founding a national institute that would coordinate the activities of all the different laboratories, not only those in the Paris area, there were laboratories all over in France. And it was also meant to trigger the collaboration and to coordinate the collaboration with CERN, who had already also a couple of years of history behind it already. So since then, the history of IN2P3 has been made by many people, by many of you who are here this evening, and I'm very happy to see you all. It has been very impressive over all the years to witness the vitality of the laboratories. Yet our work would not exist without the numerous collaborations that we have with our international colleagues and friends. I would like to thank all the speakers because we could grab today the progress that was made in our domain over the last 50 years in nuclear and particle physics, astroparticle physics, and cosmology. punctuated by the discoveries from dark energy to the Higgs boson, from neutrino oscillations to gravitational waves. We also got an idea of everything that still needs to be done. My only wish is to make it as much progress in the next 50 years than we did in the past. So, as Reynald said, unfortunately, to the sanitary situation, the cocktail we would all have enjoyed had to be cancelled, and I'm really sad about this. Especially also for all the people who prepared all these festivities, all these events, and would have highly deserved to have a drink now to relax and decompress. So thanks to all of them. Nonetheless, you may visit the museum, and the takeaway anniversary dinner box is waiting for you. The bravest among you may have a picnic outside, but don't take cold. And with this, happy anniversary, IN2P3. So who would like to say a few words, please? I know there have been some people expressing the wish to do so. Stan.
I was not prepared to this, Ursula, so I can only speak from my heart in saying that I truly congratulate IN2P3 for the 50th year. We always have a very strong and nice collaboration with NICAP in the Netherlands. And you organized a beautiful evening and a beautiful afternoon with very inspiring talks. And it is such a pity that we cannot celebrate with a glass of champagne. But nevertheless, cheers and happy anniversary.
Okay, it's my turn. Thank you very much, and happy birthday. Unfortunately, as INFN, we are a little bit older, so close to retirement in Italy. But we are working to prolong our life for over the next century. So I've seen, so we are very close institute, let's say some like twins or brother, and we have along all this period, a very solid cooperation, and I think this is very important to have to cooperate together and to make discoveries like gravitational wave. We made it together in Kashina at the EGO gravitational wave interferometer. I think that in front of us there is a very interesting period. We have listened a lot of speeches today, drawing a line to be followed in the next years. And we need to have a strong cooperation and to profit of this situation. We are coming out from a very complicated period with the pandemic. But there are many opportunities now, and we have to be able to exploit and to make a step forward to push again the frontier of knowledge. So I'm very happy to be here. I make a virtual chin-chin, and all the best, and looking forward to the future. Happy birthday.
So, I really have two very different sides to my being here. There's one very personal. I've had a personal, very tight relation with groups from IN2P3 throughout my entire career. And in particular, I had the honor of serving in a number of committees, including the Scientific Council of IN2P3 for many years, and always to appreciate the really science-driven spirit of the institution, which is, I think, the essential point, that we are curiosity-driven, driven by the will to have discoveries. And on the other side, I now here as the director of GSI and FAIR, and you know that IN2P3 is also the driver of the French presence in a number of international institutions, and in particular is one of the owners of the laboratory which I direct. So I am in some sense also an IN2P3 laboratory because we are owned by IN2P3, and I must say from the very foundation of FAIR, IN2P3 has been playing a major role in all aspects, in the definition of the physics program, in the development of the concept, in the technology which is used, and ultimately in the presence in the science. So we are extremely happy of this cooperation, which was preceded by many, many years of exchanges between GSI and many French laboratories, Ganil more than anybody else, but of course, in general, many French laboratories. And we look forward to many more years of work together and a lot of good science to do together.
Hello, everybody. I'm been forced into this position, but I'll try to do my best. For those of you who don't know me, I'm from Ganil. So as you know, Ganil is one of the biggest nuclear physics lab in France. I'm sorry. So IN2P3, and CA are the one who run Ganil. And thanks to the support of IN2P3, I think nuclear physics is doing great in France. And as you can see, one thing very special of IN2P3 is the number of foreigners that are there in IN2P3. As you can see, I don't think I look French. And I think one of the strengths of IN2P3, like all of us are here from different countries, is that within IN2P3, I think more than 25% are non-French. And I think that's a very, very important thing, especially since we are an international organization working with everybody around the world. So I'm sure this will continue, and thank you once again for coming and joining us for this very important occasion.
So good evening, I'm Giovanni Losurdo, I am the spokesperson of the Virgo collaboration. So I'm really glad to be here. And on behalf of Virgo, I would like to express my gratitude to IN2P3 for all they have done for us in the last decades. I must say that investing financial and human resources on a gravitational wave experiment in the 90s required a lot of long-term vision because you know, it was about an institute whose core business was basically particle physics, high energy physics, and having the courage to invest in a completely different field, which was not using neither calorimeter or silicon detectors, but instead were using a laser beam and suspended mirrors, was really something requiring long-term vision. Now you know how the story ended. We are publishing really great science still 5 years after the first detection, but in fact it's not the end of the story. It's instead a beginning of a new era in the observation of the universe, and I'm sure that we will continue together with IN2P3 on this road for many years to come. Thank you.
So Ursula has identified me as a representative of the United Kingdom here. I don't know whether there's anybody else here. It's been difficult, of course, to come across the channel, which doesn't separate us but unites us in Europe. I'm also actually spokesperson of Dune right now, and I just checked in my biographies that every single major experiment I've worked on was an experiment where IN2P3 played a major role. And on Dune, where we built the detectors right now, and I know that IN2P3 physicists are working hard right now at CERN to get these detectors, especially the second FAR detector, which will be largely built by IN2P3 institutes, to get this detector built and do the R&D for it. So it's been a pleasure to work with physicists and colleagues, and as all the other previous speakers, I regret I'm already getting a little weak, I have to say. Probably need some sugar to that we haven't been able to have a drink and food yet. And I'm looking forward to our picnic outside, which we'll have afterwards. Thanks very much for inviting us here and for this beautiful day.
So if there's no one else who dares to speak, 1, 2, 3, then it's closed. And well, take care, happy holidays, and bon appétit.